Most of us grow up with a simple idea about telescopes. They make distant things appear closer. A larger telescope gathers more light, reveals fainter objects, and allows astronomers to see farther into space. But in astronomy, distance has an unusual consequence. Light does not arrive instantly. When a telescope observes something far away, it is not seeing that object as it exists now. It is seeing an earlier version of it. The farther the light has travelled, the deeper the telescope reaches into the past. For the James Webb Space Telescope, this is not merely an interesting consequence of astronomy. It is the principle around which much of the observatory was designed. Webb can collect light that began travelling toward us more than 13 billion years ago. Some of those photons started their journey when the universe was only a small fraction of its present age, long before Earth existed, before the Sun formed, and before the Milky Way had developed into the galaxy we recognize today. Yet this creates a quiet paradox. The farther into the past astronomers try to see, the more difficult that past becomes to observe. The expansion of the universe stretches ancient light during its journey. Radiation that may once have been emitted at visible or ultraviolet wavelengths can arrive at Earth shifted far into the infrared. Meanwhile, cosmic dust can hide young stars and developing galaxies from telescopes designed primarily for visible light. So seeing farther does not simply require a larger version of an ordinary telescope. It requires a different kind of observatory. Webb was built around this problem. Its enormous segmented mirror gathers extremely faint radiation. Its instruments are designed primarily for infrared astronomy. Its vast sun shield helps keep those instruments cold. And instead of circling Earth close to home, Webb operates roughly 1.5 million kilometers away, near a gravitational region known as the Sun-Earth L2 point. Almost every unusual feature of the spacecraft exists because ancient light is extraordinarily difficult to measure, and that light carries information astronomers cannot obtain in any other way. Somewhere within Webb's observations may be evidence of how the earliest generations of galaxies assembled, how stars transformed simple primordial material into heavier elements, how black holes appeared in the young cosmos, and how planetary systems elsewhere developed environments unlike anything in our own solar system. But Webb does not photograph the beginning of the universe itself. There is a limit to how far backward even this telescope can look, before the first stars existed. The cosmos passed through an era without starlight. Earlier still, the universe was filled with hot plasma through which light could not travel freely. The oldest electromagnetic radiation we can observe comes from a time roughly 380,000 years after the Big Bang. Preserved today as the cosmic microwave background, Webb was not designed to see that radiation. Its territory lies later. It searches the long transition from cosmic darkness toward the first luminous structures, and then follows their descendants across billions of years. This distinction matters because the phrase looking back in time can sound almost magical. Nothing about Webb violates the ordinary behavior of light. The telescope is not traveling into the past, nor is it watching history unfold from outside time. It simply waits for old light to arrive. A photon entering Webb's mirror today may have crossed expanding intergalactic space for most of cosmic history. It may have passed through regions that would eventually become enormous clusters of galaxies. It may have travelled while generations of stars were born and died, while the sun formed, while Earth cooled, and while life developed on one small planet. Only at the end of that journey does it encounter 18 gold-coated mirror segments floating in space. There, the photon becomes a measurement, and from enough measurements, astronomers attempt to reconstruct a vanished universe. That task is far more difficult than collecting beautiful pictures. Astronomers must determine how far away an object is, what kinds of stars it contains, how much dust surrounds it, which chemical elements may be present, and whether the light comes from stars, hot gas, an actively feeding black hole, or some combination of them. At the greatest distances, even Webb often sees only faint traces. A handful of photons can carry information from an entire galaxy. This is why Webb's history is not simply the history of a spacecraft. It is the history of a question humanity has been learning how to ask for centuries. How much of the past can light preserve? Every generation of telescope builders has pushed that question slightly farther. Galileo's early telescopic observations expanded the visible heavens. Larger ground-based observatories revealed stars too faint for the unaided eye. Photography allowed astronomers to accumulate light over time. Spectroscopy transformed points of light into sources of physical information. Eventually, telescopes escaped Earth's atmosphere entirely, and among those space observatories, one became especially important to the story that would lead to Webb. The Hubble Space Telescope revealed galaxies at distances that earlier generations could scarcely have investigated. Its deep-field observations showed that apparently empty patches of sky were crowded with remote galaxies. Hubble helped astronomers trace cosmic expansion, study stellar birth and death, examine galaxy evolution, and refine measurements of the age of the universe. Yet Hubble also encountered a boundary. The earliest galaxies were receding from us within an expanding universe. Their light had been stretched toward wavelengths where Hubble's capabilities became increasingly limited. The deeper astronomers looked, the more clearly they could see what their greatest telescope could not fully reach. That realization slowly changed the question. Instead of asking how to build another Hubble, astronomers began asking what kind of observatory would be required to explore the universe that Hubble was beginning to reveal only at its limits. The answer would demand a telescope larger than Hubble, colder than Hubble. Sensitive to wavelengths, Hubble was not primarily built to observe, and positioned in a region of space where its own planet would no longer pass repeatedly beneath it. It would eventually require decades of engineering, billions of dollars, international cooperation, repeated redesigns, technological inventions, delays, political uncertainty, and a deployment sequence unlike that of any previous major astronomical observatory. But none of those challenges explains why people were willing to attempt it. For that, we must return to the telescope that came before Webb and to an unexpected lesson hidden within some of the deepest images ever taken. Hubble had shown humanity an astonishingly rich universe. It had also shown us where the darkness began, and somewhere beyond that darkness was a chapter of cosmic history that no telescope had yet been built to read. What exactly was Hubble unable to see long before the James Webb Space Telescope opened its golden mirror to the universe? Another observatory had already transformed what people expected a space telescope to accomplish. The Hubble Space Telescope orbited only a few hundred kilometers above Earth. Compared with the distances separating planets, stars, and galaxies, it remained remarkably close to home. Yet by rising above most of Earth's atmosphere, Hubble gained something astronomers on the ground had pursued for generations: an exceptionally clear and stable view of the sky. Earth's atmosphere protects life, but it complicates astronomy. Moving layers of air distort incoming starlight, producing the familiar twinkling of stars. Water vapor and other molecules absorb portions of the electromagnetic spectrum. Clouds interrupt observations entirely. Above the atmosphere, many of these obstacles disappear. Hubble's 2.4-meter primary mirror could therefore produce observations of extraordinary precision over decades. It examined planets in our solar system, watched stars being born inside glowing nebulae, measured distant supernovae, mapped galaxies, and helped astronomers investigate the expansion of the universe. But some of its most influential observations began with something much quieter, an apparently empty patch of sky. In December 1995, Hubble was directed toward a tiny region in the constellation Ursa Major. The field had been deliberately selected because it seemed unremarkable. There were few bright foreground stars to interfere with the view. For many hours, across several days, Hubble collected light. The resulting Hubble deep field revealed thousands of galaxies. Some were relatively nearby. Others were so distant that their light had travelled for billions of years before reaching the telescope. The image offered something close to an archaeological core sample through cosmic history. Looking across the field meant looking across different eras of the universe at once. Later surveys pushed this approach still further. The Hubble Ultra Deep Field and subsequent observations reached toward increasingly faint and distant galaxies. Astronomers began assembling a picture of a cosmos whose appearance changed with time. Nearby galaxies often possessed familiar structures. Spirals stretched across enormous disks. Elliptical galaxies contained vast populations of older stars. Farther away, Corresponding to earlier cosmic epochs, galaxies frequently appeared smaller, more irregular, and more actively forming stars. The universe had not always looked the way it does today. Galaxies had histories. This may seem obvious now, but observing that history directly required astronomers to see across enormous distances. And as Hubble reached deeper, it encountered a fundamental effect of the expanding universe. Light itself was being stretched. A galaxy contains stars that emit radiation across many wavelengths. Young, hot stars can be especially bright in ultraviolet light. But if that galaxy lies sufficiently far away, the expansion of space stretches those wavelengths during the photon's journey toward us. Ultraviolet radiation can arrive as visible light. Visible radiation can arrive in the infrared. This effect is called cosmological redshift. It does not simply make distant galaxies appear redder in an ordinary photographic sense, at sufficiently large redshifts. Much of the radiation astronomers need to study moves beyond the wavelengths where a particular telescope is most effective. Hubble could observe some near-infrared light, especially after later instruments expanded its capabilities. This allowed it to detect remarkably distant galaxies, but Hubble had never been designed primarily as a deeply cooled infrared observatory. Its mirror was comparatively warm, its wavelength coverage had limits, and the earliest galaxies astronomers hoped to investigate were increasingly difficult targets. The problem became more important because of what those galaxies represented. The universe is approximately 13.8 billion years old. During its earlier stages, it contained mostly simple elements, particularly hydrogen and helium, with smaller amounts of lithium. The heavier elements familiar on Earth had not yet been manufactured in large quantities because generations of stars had not yet lived and died. At some point, gravity gathered matter into the structures from which the first stars emerged. Those stars began changing the cosmos around them. Their radiation illuminated surrounding gas. Their interiors produced new elements. Their deaths redistributed some of those materials into space. Small systems grew through accretion and mergers. Galaxies developed. Black holes appeared and, in some cases, grew with remarkable speed. Hubble could glimpse parts of this early history, but the farther astronomers tried to push, the more the universe seemed to move away from Hubble's strongest vision. There was another obstacle as well. Dust. Cosmic dust is made from tiny solid particles, often containing compounds involving elements such as carbon, silicon, oxygen, iron, and magnesium. In regions where stars are forming, dust can obscure visible light. A stellar nursery may therefore appear dark at wavelengths. Human eyes can see while becoming much more revealing in infrared observations. The same principle applies to distant galaxies. Infrared astronomy could allow researchers to investigate regions hidden behind dust, while also recovering ancient radiation shifted toward longer wavelengths by cosmic expansion. Two very different problems pointed toward the same solution: to understand both the distant universe and obscured regions of the nearer universe. Astronomers needed better infrared vision, and infrared astronomy has an inconvenient requirement. The telescope itself must be cold. Any object with a temperature above absolute zero emits thermal radiation. A telescope that is too warm can therefore produce infrared emission of its own. Trying to detect faint cosmic infrared signals with a warm telescope can become something like attempting to notice a whisper, while the instrument itself is contributing to the background noise. For certain infrared wavelengths, cooling is not merely useful, it is fundamental. Earlier space missions had already demonstrated the scientific power of infrared astronomy. Observatories such as the Infrared Astronomical Satellite, the Infrared Space Observatory, and later the Spitzer Space Telescope explored a universe that often looked profoundly different from the one visible light telescopes revealed. But the ambition forming around Hubble's successor went further. Astronomers wanted a large infrared telescope capable of examining extremely faint objects at enormous distances. That requirement immediately created engineering consequences. A larger mirror would collect more light, but a mirror large enough for the desired science could not fit inside existing launch vehicles as a single rigid piece. A cold telescope would need protection from sunlight, Earth, and the Moon. And if the observatory were placed far from Earth to maintain a stable thermal environment, astronauts would not be able to service it as they had serviced Hubble. Each scientific advantage seemed to create a new engineering difficulty. By the 1990s, astronomers were therefore approaching an unusual moment. Hubble was still young. Many of its greatest discoveries had not yet been made. Yet researchers were already discussing the telescope that should eventually follow it. They were not doing so because Hubble had failed. They were doing so because it had succeeded. Every new layer of the universe that Hubble revealed made the next hidden layer more compelling. The familiar universe was becoming larger, older, and more dynamic, and at its distant edge. The first cracks had appeared in what existing telescopes could tell us. To cross that boundary, astronomers would first have to decide what they were actually trying to find. There is a particular kind of uncertainty that appears when an instrument reaches the edge of what it can see. At first, the darkness seems empty. Then, with better observations, small structures begin to emerge. The James Webb Space Telescope was conceived in that transition, when astronomers were beginning to understand that the early universe was not simply invisible. It was visible in principle, but much of its light had been shifted, absorbed, or diluted beyond the practical reach of existing observatories. The first cracks in the familiar picture were not caused by one surprising image. They accumulated gradually. For much of the 20th century, astronomers had developed a broad sequence for cosmic history. The universe began in a hot, dense state. It expanded and cooled. Matter gradually gathered under gravity. Eventually, stars formed. Stars assembled into galaxies. Galaxies grew and merged, producing increasingly complex structures. The broad framework remains extraordinarily successful, but the details were much less certain. Astronomers did not know precisely when the first stars formed. They did not know exactly how the earliest galaxies assembled. They did not know how quickly galaxies could grow in the first few 100 million years. And they had limited observations of the period when the first luminous structures transformed the young cosmos. This interval is sometimes called cosmic dawn. It occupies a small portion of the universe's enormous history, but it contains one of the most important transitions in cosmic evolution. Before the first stars, there was no starlight. There was hydrogen gas, gravity, dark matter, and an expanding universe. Then somewhere, somehow, matter became dense enough for the first stars to ignite. The moment was not a single universal flash. Stars formed in different places at different times. Small groups of stars emerged inside growing structures, and their radiation gradually changed the surrounding environment. This eventually contributed to the epoch known as rionization, when energetic radiation transformed much of the neutral hydrogen between galaxies. Yet the exact sequence remained difficult to reconstruct. One reason was simple. The first galaxies were expected to be extremely faint. A galaxy containing a small population of young stars billions of light years away can send only a tiny number of photons toward Earth. Those photons are also spread across enormous distances, while the expansion of the universe shifts their wavelengths. The further back astronomers looked, the more demanding the observation became. Then another problem appeared. Some observations seemed to suggest that galaxies had already become surprisingly developed relatively early in cosmic history. This did not necessarily contradict the standard model of cosmology. The model does not require galaxies to remain primitive for a long time, but the observations raised questions about how efficiently matter could collapse and form stars in the young universe. Hubble and other observatories had already identified galaxies at very high redshift. Ground-based telescopes and infrared instruments added further evidence. Astronomers developed increasingly sophisticated methods for estimating distances and ages, yet there was a limit. The farther galaxies were pushed into the early universe, the more their strongest light moved toward infrared wavelengths. This was precisely where the planned successor to Hubble would become most powerful. But Webb was still only a concept. Its history began decades before launch, through discussions about what the next major space observatory should accomplish. In the early planning stages, the project was known by another name, the Next Generation Space Telescope. The scientific motivation was broad. Astronomers wanted to observe the first galaxies. They wanted to understand star and planet formation. They wanted to study the physical and chemical properties of distant worlds. They wanted to examine objects hidden behind cosmic dust. These goals were connected by a common requirement: a large sensitive infrared telescope operating in an exceptionally cold environment. The basic idea sounded reasonable. Building it was anything but. As engineers examined the requirements, the telescope became a collection of difficult problems. The primary mirror needed to be far larger than the mirror of Hubble, but a large, rigid mirror could not simply be placed inside a launch vehicle. So the mirror had to be divided into segments. Those segments would need to survive launch independently, and then be positioned with extraordinary accuracy after reaching space. The observatory would also need to remain cold. A giant sunshield was proposed, but a shield large enough to protect the telescope could not remain permanently extended during launch. It would need to fold, and after launch, it would need to unfold in space. This introduced a new category of risk. A conventional spacecraft can often tolerate a malfunction in one component, because another system may perform the same function. Webb's deployment architecture was different. Many mechanisms were connected in sequence. A latch had to release, a cover had to move, a membrane had to deploy, a cable had to travel, a motor had to operate, a mirror segment had to reach its correct position. The spacecraft was effectively carrying a folded structure that had to become a fully functioning observatory without human hands nearby. Every additional mechanism created another opportunity for failure, and there was no practical way to send astronauts to repair it. That last point represented one of the greatest departures from Hubble's history. Hubble had been designed with servicing missions in mind. Astronauts could visit the telescope, replace instruments, repair equipment, and upgrade its capabilities. Webb would travel far beyond the region where such missions could be performed using existing human spaceflight systems. Once launched, its fate would largely be sealed. The telescope therefore had to work as delivered. This changed the philosophy of testing. Engineers could not simply prove that each component worked individually. They had to understand how hundreds of components would behave together, and because the spacecraft was designed to operate at extremely low temperatures, some testing had to reproduce the conditions of space as closely as possible. The scale of the undertaking grew. So did the cost. So did the schedule. The project passed through design revisions, delays, technical difficulties, and political scrutiny. Its name eventually changed. The next generation space telescope became the James Webb Space Telescope, honoring James E. Webb, who had served as NASA administrator during the Apollo era. The name would become attached to a spacecraft that did not yet exist in its final form. Meanwhile, the scientific questions continued to sharpen. If the earliest galaxies were faint, Webb needed enormous light-gathering power. If their light had been redshifted, Webb needed sensitive infrared instruments. If dust concealed star formation, infrared observations could reveal regions hidden from visible light. If planetary atmospheres were to be studied, the telescope needed spectrographs capable of separating light into detailed patterns. The observatory was therefore becoming more than a successor to Hubble. It was becoming a machine designed around a particular idea. The universe leaves clues in light, but those clues arrive transformed by distance, expansion, dust, temperature, and time. To read them, astronomers would need to collect the faintest signals while keeping the telescope itself almost silent in the infrared. The science had defined the challenge. Now engineering had to answer it. And the next question was no longer what Webb should observe. It was whether humanity could actually build a telescope capable of doing it. In the middle of the 1990s, astronomy was changing in two very different directions. One direction pointed outward, toward the oldest galaxies that telescopes could barely detect. The other pointed toward nearby stars and an entirely different question. Were there planets around other suns? For most of human history, planets beyond the solar system belonged to philosophy and speculation. The idea was plausible, but plausibility was not evidence. Then, in 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the Sun-like star 51 Pegasi. The planet was not seen directly. Instead, astronomers detected the subtle gravitational influence it exerted on its star. As the planet travelled around the star, its gravity caused the star to move slightly back and forth. That motion shifted the star's spectral lines through the Doppler effect. By measuring those changes, astronomers could infer the presence of an unseen companion. The planet, now known as 51 Pegasi b, was an extraordinary object. It was a gas giant orbiting extremely close to its star, completing an orbit in only a few days. That orbit was nothing like the one followed by Earth. The discovery therefore did more than add another planet to a growing catalogue. It demonstrated that planetary systems could be arranged in ways that had not been expected from the architecture of our own solar system. The discovery also revealed an important principle of astronomy. Sometimes the object itself is not what we measure. We measure its effect on something else. A star's motion can reveal a planet. A spectrum can reveal an atmosphere. A tiny change in brightness can reveal an eclipse. A faint infrared feature can reveal a chemical molecule. The universe often announces the presence of distant things indirectly. This would become central to the scientific ambitions of Webb. A telescope capable of observing planets around other stars would not necessarily need to photograph those planets as bright worlds. Instead, astronomers could study their light. When a planet passes in front of its star, a tiny fraction of the starlight can pass through the planet's atmosphere before reaching the telescope. The atmosphere absorbs particular wavelengths more strongly than others. Those missing wavelengths form a pattern. From that pattern, astronomers can investigate atmospheric composition. The measurement is delicate. The star may be thousands or millions of times brighter than the planet. The atmosphere may contribute only a tiny fraction of the total signal. Yet the principle is powerful. A world too distant to photograph in detail can still reveal something about its chemistry. This same idea of reading information from light appears everywhere in astronomy. Spectroscopy had already transformed the study of stars. By separating light into its component wavelengths, astronomers could identify elements and infer temperature, density, motion, and other physical properties. For Webb, spectroscopy would become one of its most important tools. The telescope would not simply collect beautiful infrared images. It would divide light into patterns that could be interpreted scientifically. But the discovery of 51 Pegasi b introduced another possibility. Perhaps planets were not rare exceptions. Perhaps they were common. As observational techniques improved, thousands of exoplanets would eventually be identified. Some would be gas giants, others would be rocky worlds. Some would orbit their stars in only a few days, others would take years. The diversity was remarkable, and it changed the question. Astronomers no longer needed to ask only whether planets existed elsewhere. They could begin asking what those planets were like. Could some possess atmospheres? Could clouds form there? Could their chemistry be different from anything in our solar system? Could a rocky planet orbit at a distance where liquid water might persist on its surface? These questions were far more difficult than simply detecting a planet. They required information about a world that might be many light years away. Webb would eventually become one of the instruments capable of pursuing those questions. But there was another discovery from the same era that would shape its story in a different way. Astronomers were learning that the universe itself was not behaving quite as simply as expected. In the late 1990s, two independent teams studying distant Type Ia supernova found evidence that cosmic expansion was accelerating. The observations were subtle. These particular supernovae could be used as approximate distance indicators because their intrinsic brightness could be calibrated. By comparing how bright they appeared with how their light had been redshifted, astronomers could estimate how the expansion of the universe had changed over cosmic time. The results suggested something profound. The expansion of the universe was not merely continuing, it was accelerating. The leading interpretation introduced a component now called dark energy. Yet dark energy remains one of the deepest unresolved problems in modern cosmology. We know that something causes the observed expansion history. We do not know its fundamental nature. It could be associated with the energy of empty space. Or perhaps the observations reflect a deeper modification of our understanding of gravity on cosmic scales. The distinction matters. Astronomy often advances by measuring what the universe does before knowing why it does it. Webb belongs to that tradition. Its mission was never simply to confirm a complete theory. It was designed to gather observations capable of testing theories. The discoveries of the 1990s therefore created a remarkable scientific landscape. At one extreme, astronomers were looking toward the earliest galaxies and the origins of cosmic structure. At another, they were discovering planets around distant stars and considering the chemistry of other worlds. Between those scales lay stars, nebulae, black holes, galaxies, and the evolution of matter itself. A single observatory could not answer every question, but an infrared telescope with an enormous mirror could contribute to many of them. The scientific case for Webb was becoming broader and more compelling, yet every new goal increased the technical demands. Studying distant galaxies required sensitivity. Studying planetary atmospheres required precision. Studying cool objects required a cold telescope. Studying the earliest universe required observations at wavelengths that had been stretched by cosmic expansion, and all of this had to happen from space. The telescope being designed was therefore becoming a compromise between ambition and physical reality. The mirror had to be enormous, but it had to fit inside a rocket. The instruments had to be extremely sensitive, but the spacecraft had to survive launch. The observatory had to remain cold, but it had to operate near the sun, and once deployed, the telescope would be far beyond the reach of astronauts. The scientific questions had become clearer. The universe had become stranger, but the telescope itself had become one of the greatest engineering challenges in the history of astronomy. To understand why Webb looks the way it does, we now have to leave the stars for a moment and examine the machine itself, because almost every unusual feature of that golden mirror and enormous silver shield was created to solve one particular problem. How do you build a telescope that must remain cold, enormous, precise, and folded until the moment it reaches space? A telescope is usually defined by its mirror. The larger the mirror, the more light it can collect. More collected light means fainter objects become detectable, and fine details become easier to distinguish. For Webb, this basic principle created a problem almost immediately. Hubble's primary mirror measures 2.4 meters across. Webb's primary mirror measures approximately 6.5 meters. That difference is enormous. A 6.5-meter mirror would gather far more light than Hubble's mirror, but it could not simply be placed inside a launch vehicle as one solid piece. The solution was to divide it into segments. Webb's primary mirror consists of 18 hexagonal segments arranged together to form a single large optical surface. Each segment is made from beryllium, a material chosen because it is lightweight and behaves predictably as it cools to extremely low temperatures. The segments are coated with a thin layer of gold. The gold is not decorative. Gold reflects infrared radiation particularly well, making it useful for Webb's wavelength range. The result is the distinctive golden appearance that has become inseparable from the telescope. But 18 mirrors create a problem that one mirror does not have. They must behave as one. A conventional telescope mirror can be polished into a single continuous surface. Webb's mirror has separate pieces, each mounted on its own structure and controlled by tiny actuators. After launch, those segments had to be moved into position and aligned with extraordinary precision. The required accuracy is measured in fractions of a wavelength of light. At first glance, this may sound like a mechanical problem. It is actually an optical one. If one segment is slightly displaced, light arriving from a distant star will not converge at exactly the same point as light reflected by its neighbours. Instead of producing one sharp image, the telescope would produce multiple overlapping images. The 18 pieces would behave like 18 imperfect telescopes. So Webb needed a way to transform those separate mirrors into one optical system after reaching space. That was only one half of the challenge. The other was temperature. Infrared astronomy is sensitive to heat. Everything with a temperature above absolute zero emits thermal radiation. Webb's instruments needed to detect extremely faint infrared signals from astronomical sources, so the observatory itself had to produce as little unwanted infrared radiation as possible. This is why Webb does not resemble Hubble. Hubble is a relatively compact cylinder, with its instruments and mirror exposed to the space environment. Webb has an enormous barrier between its telescope and the Sun. The Sun shield, its 5 thin layers of specialized membrane material, unfold into a structure roughly the size of a tennis court. The purpose is simple: block sunlight. The effect is profound. The side facing the Sun can become very warm, while the telescope side remains dramatically colder. The layers are separated from one another, allowing heat to radiate away as it moves through the structure. The shield does not work like a thick blanket. It works more like a series of barriers. Each layer intercepts sunlight and re-radiates some of that energy towards space. By the time the heat reaches the telescope side, very little remains. The spacecraft therefore maintains a permanent division between two thermal environments. One side faces the sun, the other faces darkness. That orientation is crucial. Webb operates near the second Sun-Earth Lagrange point, known as L2, approximately 1.5 million kilometers from Earth on the side opposite the Sun. L2 is not a place where gravity disappears. Instead, it is a region where the gravitational influences of the Sun and Earth, combined with the spacecraft's orbital motion, allow an object to maintain a useful position relative to Earth as both travel around the Sun. Webb does not sit motionless at L2. It follows a large orbit around the point. From this location, the Sun, Earth, and Moon remain on roughly the same side of the spacecraft. That makes the sun shield far more effective. One side of Webb can remain directed toward these sources of heat, while the telescope remains pointed toward deep space. This geometry also allows the observatory to communicate with Earth. But placing Webb at L2 created another consequence. There would be no practical servicing mission like those that repeatedly visited Hubble. The telescope had to survive launch, deployment, commissioning, and years of operation without astronauts physically repairing it. That requirement influenced almost every component. Even the mirror segments had to fold. The left and right portions of the primary mirror could swing inward during launch, reducing the telescope's width enough to fit inside the Ariane 5 rocket that would carry it into space. The enormous sun shield had to fold as well. Its 5 layers were carefully packed into a compact arrangement. During launch, the entire observatory was enclosed within the rocket's protective fairing. This created a strange transformation. On Earth, Webb was a folded machine. In space, it needed to become an enormous observatory. The difference between those two states was not a simple mechanical extension. It involved hundreds of individual release mechanisms, motors, cables, pulleys, hinges, bearings, latches, and electrical commands. Some components existed only to release another component. Others existed to guide a structure into position. Still others were backups in case the first mechanism did not behave as expected. The deployment sequence was therefore built around redundancy where possible. But redundancy could not eliminate the fundamental risk. If a critical mechanism failed, there might be no second opportunity. This was particularly true of the sun shield. Its membranes were delicate by necessity. They had to be thin enough to remain lightweight and flexible, yet strong enough to survive launch and unfold correctly in space. Their deployment depended on controlled tension. The membranes had to separate. They had to spread. They had to reach their final geometry without becoming trapped or damaged. And all of this had to occur hundreds of thousands of kilometers from Earth. The telescope's design therefore contained a remarkable contradiction. The greater its scientific ambition became, the more delicate the machine had to be. A giant mirror needed to be segmented. A huge thermal barrier needed to be thin. A precision observatory needed to fold. A spacecraft designed to observe faint heat had to survive the intense thermal environment of launch, and then rapidly become cold. Every solution created another problem, and every problem had to be solved before the telescope ever left Earth. By the time Webb's design matured, it was no longer merely a larger infrared telescope. It was a spacecraft that had to perform a carefully choreographed transformation in space. The most important parts of the telescope were not simply carried into orbit. They had to be unfolded there. That meant the launch would not be the moment when Webb was truly ready to observe. It would only be the beginning. The real test would come afterward, when the folded observatory had to open itself piece by piece, travel toward L2 cool down, align 18 mirrors, and prove that the entire architecture worked. Only then could the golden mirror begin collecting the ancient light for which it had been built. There is a particular reason the James Webb Space Telescope had to become so large. The earliest galaxies are not merely far away, they are faint. That distinction is easy to overlook. A distant galaxy can contain billions of stars and still appear to a telescope as an extraordinarily weak source of light. The farther away it is, the more its radiation spreads before reaching the observer, and when the universe itself expands during that journey, the light becomes stretched toward longer wavelengths. This is where Webb's enormous mirror becomes essential. A telescope's primary mirror acts as a light collector. A larger collecting area means more photons can be gathered during an observation. Webb's mirror, approximately 6.5 meters across, has more than 6 times the light collecting area of Hubble's 2.4-meter mirror. That does not mean Webb makes distant galaxies appear 6 times closer. It means something subtler. It allows astronomers to collect enough light from extremely faint sources to measure them. And measurement is where the story becomes interesting. A photograph of a distant galaxy can tell us where it is and what its overall structure looks like. A spectrum can tell us much more. Light can be separated into a range of wavelengths, producing a spectral pattern. Atoms and molecules interact with radiation in characteristic ways. They absorb or emit particular wavelengths, leaving signatures that can be studied by astronomers. The spectrum of a distant galaxy can therefore reveal its chemical composition, temperature, motion, star formation activity, and redshift. But there is a difficulty. The earlier the galaxy, the more strongly its light has been shifted. Consider a simplified example. Suppose a young galaxy emitted a particular feature in ultraviolet light. As the universe expanded, the wavelength of that radiation became longer. By the time the light reached Earth, the same feature might appear in the infrared. The information was not destroyed. It had been transformed. Webb was designed to detect that transformed information. This makes the telescope something more precise than a powerful camera. It is an instrument for recovering ancient physical evidence. The photons arriving at its detectors have travelled across cosmic time, carrying traces of conditions that existed billions of years ago. Yet there is another reason the earliest universe is so difficult to study. The first stars did not form inside empty space. They formed within gas and dark matter. Dark matter does not emit or absorb light in the ordinary way, but its gravitational influence helped create the structures in which ordinary matter accumulated. Gas cooled. Gravity pulled material together. Eventually, some regions became dense enough for stars to form. The first stars were probably very different from the Sun, because the early universe contained very little of the heavier elements that later generations of stars inherited. The first stars are expected to have formed from gas dominated by hydrogen and helium. Their properties remain an active area of research. Some models predict that the earlier stars were extremely massive compared with the Sun. Others explore a broader range of masses and formation environments. Whatever their exact characteristics, their existence would have altered the young universe. Stars emit ultraviolet radiation. The first generations therefore began transforming their surroundings. They also manufactured heavier elements inside their interiors. When massive stars ended their lives, some of those elements were returned to surrounding space. The next generations of stars could then form from material enriched by previous stellar evolution. Over time, the universe became chemically richer. Carbon, oxygen, silicon, iron, and many other elements. Eventually, these elements became part of planets, rocks, atmospheres, and living organisms. The atoms in a human body are therefore connected to a cosmic history that began long before Earth. But Webb's task is not to tell this story as a finished narrative. It is to find evidence for each stage. That distinction becomes important when astronomers observe extremely distant galaxies. Suppose Webb detects a galaxy from a time when the universe was only a few 100 million years old. The detection itself is a fact. The galaxy exists in the observed data. Its estimated distance can be constrained through redshift measurements. Its spectrum may reveal particular emission lines. Its brightness and structure can be measured. But conclusions about its history require interpretation. Astronomers might infer that it contains young stars because of the shape of its spectrum. They might estimate its stellar mass using models. They might infer rapid star formation. Each step introduces assumptions. The farther astronomers look, the more important those distinctions become. A telescope does not directly photograph the first galaxy. It records light. Scientists then reconstruct what kind of object could have produced that light. This is one reason Webb's discoveries must be interpreted carefully. Early observations sometimes produce headlines suggesting that galaxies appeared too early or were too mature. But astronomy rarely resolves such questions from a single observation. Distance estimates may change. Dust may alter apparent brightness. A galaxy's light can contain contributions from stars and active black holes. Stellar populations can be difficult to distinguish. And theoretical models of galaxy formation continue to evolve. Webb provides new evidence. it does not automatically provide the final interpretation. This is especially important because the early universe contains another mystery. How did the first galaxies become visible? The cosmic environment around them was initially filled with neutral hydrogen. Ultraviolet radiation from the earliest stars and galaxies gradually changed that gas. The process of reionization did not happen everywhere at once. It unfolded over cosmic time, creating expanding regions where energetic radiation had altered the surrounding hydrogen. Eventually, much of the intergalactic medium became ionized. Webb is helping astronomers investigate the sources of the radiation involved in this transformation. Were relatively small galaxies responsible? Were larger systems more important? Did black holes contribute significantly? How rapidly did the transition occur? The answers are still being refined. And this is where the telescope's central mystery becomes deeper. Webb was built partly to find the first luminous structures, but finding them is only the beginning. Astronomers also need to understand how those structures transform the universe around them. The first stars were not passive lights in a dark background. They became agents of cosmic change. Their radiation altered gas. Their deaths redistributed elements. Their gravity helped build larger systems. Their descendants eventually contributed to the galaxies we see today. The telescope therefore reaches backward not simply to discover ancient objects, but to investigate the first stages of a chain of events that eventually produced a universe capable of containing planets, chemistry, and life. And yet there is a question even deeper than the formation of the first galaxies. If the universe was so young when some of these structures appeared, how quickly could gravity have assembled them? How much matter was already concentrated into small dark matter halos? How efficiently could gas cool and form stars? And could the earliest galaxies have grown faster than our simplest models predicted? To answer those questions, astronomers must follow the evidence carefully. The first great mystery is no longer merely whether Webb can see far enough. It is what the ancient universe looked like when the first lights began to appear. The first great mystery of Webb is not solved by finding one ancient galaxy. It is solved, if it can be solved at all, by comparing many observations. A single distant object can be unusual. A population of distant objects begins to reveal a pattern. That is why the work of the James Webb Space Telescope is so closely connected with surveys. Astronomers do not simply point Webb at the most interesting object they can find. They also observe carefully selected regions of the sky, measuring large numbers of galaxies across different distances and wavelengths. Each observation becomes another point on a cosmic timeline. The farther away the galaxy, the earlier in cosmic history we see it. This allows astronomers to arrange galaxies approximately in chronological order. A galaxy seen 10 billion light-years away is not simply farther than a galaxy seen 5 billion light-years away, because its light has taken longer to reach us. We are also seeing an earlier stage of cosmic history. The telescope therefore turns distance into time, and once distance becomes time, a collection of galaxies becomes something like a sequence of ancient snapshots. But the sequence is incomplete. We cannot watch one galaxy continuously from birth to maturity. Instead, we observe different galaxies at different stages and try to reconstruct the overall history from the population. This is similar to studying a human life by observing thousands of people of different ages. No individual provides the entire story, but together they can reveal patterns of growth and change. Astronomers apply the same logic to galaxies. Webb's observations can measure their brightness, shapes, colors, spectra, star formation, chemical composition, and distances. One of the first steps is determining how far away an object is. For galaxies at enormous distances, redshift becomes particularly important. As space expands, the wavelength of light traveling through it is stretched. The amount of stretching provides information about how much the universe expanded while that light was in transit. Astronomers describe this using redshift, commonly represented by the letter Z. A higher redshift generally corresponds to a more distant and earlier object, although the relationship is cosmological rather than a simple ruler measurement. Once the redshift is known, astronomers can estimate the epoch in which the observed light was emitted. But measuring redshift is not always easy. For some galaxies, a spectrum contains recognizable emission or absorption features that provide a relatively secure measurement. For extremely faint sources, however, obtaining a detailed spectrum can require long observations. Sometimes astronomers begin with imaging. An object may appear bright in one infrared filter and much fainter in another. This pattern can provide an estimated redshift. Such estimates are called photometric redshifts. They are useful, but they are not identical to spectroscopic measurements. A galaxy with an unusual combination of dust, stellar populations, or emission lines can sometimes imitate the colours expected for a much more distant object. This is why spectroscopy is so valuable. It gives astronomers more direct physical clues. Webb's instruments include spectroscopic capabilities specifically designed to separate faint infrared light into its constituent wavelengths. The near-infrared spectrograph, or an IR spec, can observe many objects and analyze their spectra. The near-infrared camera, NIRCam, provides high-resolution imaging and is also essential for locating distant galaxies. The mid-infrared instrument, MIRI, extends Webb's observations into longer infrared wavelengths, revealing cooler material and processes that are difficult to detect at shorter wavelengths. Together, these instruments allow astronomers to approach the same object from different directions. An image shows structure. A spectrum reveals physical signatures. Different wavelengths reveal different components. And when these measurements agree, confidence grows. This matters particularly in the study of the early universe. Suppose astronomers find a faint galaxy that appears to be extremely distant. The first question is whether the distance estimate is reliable. The next is what the galaxy contains. Is its light dominated by young stars? Is there evidence of older stellar populations? Is dust present? Are there strong emission lines from ionized gas? Is an active black hole contributing to the radiation? These questions can transform a small patch of infrared light into a physical story. One of Webb's great strengths is that it can examine galaxies that earlier telescopes could detect only as extremely faint sources. But even then, interpretation requires caution. A galaxy's observed brightness does not directly tell us its total mass. Astronomers must model the stellar population, dust, star formation, and other contributors. A bright galaxy might contain many stars, or it might contain a smaller stellar population producing unusually intense radiation. An active galactic nucleus could also contribute significantly. The early universe is especially difficult because the galaxies being observed are young. Their stellar populations may be dominated by short-lived, massive stars. Those stars emit large amounts of ultraviolet radiation. That radiation can ionize surrounding gas, producing bright emission lines. The result can make a young galaxy appear extraordinarily luminous in particular wavelengths. This introduces an important distinction. A galaxy can be bright without necessarily being massive. Brightness and mass are related, but they are not interchangeable. As Webb began producing observations of distant galaxies, astronomers therefore had to examine the measurements from several perspectives. The question was not simply, how bright is this galaxy? It was, what physical conditions could produce the light we observe? That question leads naturally toward galaxy formation. The standard picture begins with small concentrations of dark matter. Gravity gathers matter into halos. Ordinary gas falls into these gravitational wells. As the gas cools, it can become dense enough for stars to form. Stars then produce radiation and stellar winds. Massive stars eventually explode or shed material. Black holes may grow within galaxies. Galaxies merge. Over time, small systems become larger and more complex. This process is not a single smooth construction project. It is more like a continuously changing network of interactions. And Webb is looking at a period when many of these processes were already underway. That is one reason some early galaxies can appear surprisingly developed. The universe was young, but galaxy formation had already begun. The question is how rapidly. Modern cosmological simulations can model this evolution. They begin with assumptions about the distribution of matter and the laws governing gravity, gas, star formation, and feedback. Then computers evolve those systems forward through cosmic time. The resulting virtual universe can be compared with observations. If the simulated galaxies resemble the real ones, the model gains support. If observations repeatedly differ from simulations, scientists must investigate why. Perhaps the simulations are missing an important physical process. Perhaps the observations are being interpreted incorrectly. Perhaps galaxies form more efficiently than expected under certain conditions. Or perhaps the underlying cosmological assumptions need refinement. This is the scientific value of Webb. It is not merely producing a larger collection of beautiful images, it is placing new measurements into a long-running conversation between observation and theory. And the earliest galaxies provide an unusually demanding test. They formed when the universe had much less time to build complex structures. If large, luminous galaxies are common at very early times. Astronomers need to understand how they assembled so quickly, but if only a small fraction are unusually bright, the apparent tension may be less profound. Population statistics therefore matter. One extraordinary galaxy can attract attention. 1,000 galaxies can reveal whether that object was exceptional. This is why surveys are so important. They allow astronomers to move from individual discoveries toward cosmic demographics. How many galaxies existed at a particular epoch? How bright were they? How rapidly were they forming stars? How much did their numbers change as the universe aged? When did the population of galaxies begin increasing rapidly? When did the first systems become chemically enriched? And which galaxies contributed most to the transformation of the intergalactic medium? Each answer creates another question. The deeper Webb looks, the less the early universe resembles a blank beginning. Instead, it becomes a landscape of processes already underway. Stars were forming, galaxies were growing, black holes were feeding, gas was changing, elements were accumulating. The cosmos was already becoming structurally complex, but there is still a boundary. At some point, the galaxies become too faint, too small, or too rare for current observations to characterize reliably. Beyond that boundary lies an era in which the first luminous structures were beginning to emerge. That is where the central mystery becomes sharper. What exactly happened between a nearly starless universe and the first generation of galaxies bright enough for Webb to detect? And could the earlier structures have formed in ways that our present models do not yet fully capture when a new telescope reveals something unexpected? There are usually several possible explanations. The first possibility is that the observation is wrong. The second is that the observation is correct, but the interpretation is incomplete. The third is that the existing theory is broadly correct, yet some part of the model needs to be adjusted, and only after these possibilities have been carefully examined does anyone seriously consider whether the underlying theory itself might need to change. This hierarchy is especially important when studying the earliest galaxies with the James Webb Space Telescope. Some early observations appeared to show surprisingly bright galaxies at very high redshifts. Because redshift allows astronomers to estimate how far back in cosmic history the light originated, these galaxies seem to exist when the universe was only a few 100 million years old. That created an intriguing question. How could galaxies become so luminous so quickly? The question sounds simple. The answer is not. Brightness does not have a single cause. A galaxy can appear bright because it contains a large population of stars. It can also appear bright because many of those stars are extremely young and massive. Gas surrounding the stars can produce strong emission lines. An active black hole can contribute enormous amounts of radiation. Dust can alter which wavelengths escape. So the first step is not to declare that an early galaxy is unexpectedly massive. The first step is to determine what is actually producing the light. This is where Webb's spectroscopic observations become essential. A spectrum can reveal emission features associated with ionized gas. It can also provide information about the stars and other energetic processes within a galaxy. The more information astronomers obtain, the less freedom there is for competing explanations. But uncertainty never disappears completely. Consider one possible interpretation. Perhaps some early galaxies simply formed stars with extraordinary efficiency. In the modern universe, star formation is often relatively inefficient. Much of the gas available to a galaxy does not immediately become stars. Turbulence, magnetic fields, stellar winds, radiation, and supernova explosions can prevent gas from collapsing continuously in a young galaxy with different physical conditions. However, some of those processes may operate differently. If gas could collapse rapidly, a relatively small amount of material might produce a large population of young stars. The resulting galaxy could therefore be bright without being as massive as its brightness initially suggests. This possibility fits comfortably within the broad framework of modern cosmology. It would not require a new theory of gravity or a new description of the universe. It would require better understanding of how stars form under early cosmic conditions. A second possibility involves black holes. Most large galaxies today contain supermassive black holes at their centers. When gas falls toward one of these objects, friction and gravitational energy can produce intense radiation. Such an active galactic nucleus can make a galaxy appear much brighter than its stars alone would suggest. This creates an important complication. A distant source that looks like a massive galaxy might partly be the glow of a rapidly feeding black hole. But then another mystery appears. If black holes were already massive in the early universe, how did they grow so quickly? A black hole can increase its mass by consuming gas and merging with other black holes. Yet there are physical limits to how rapidly sustained accretion can normally proceed. Radiation produced by infalling material can eventually push back against additional gas. This creates a growth problem. If some early black holes reached enormous masses surprisingly soon after the Big Bang, their seeds may have needed to begin larger than the black holes that form from ordinary massive stars today. Or they may have experienced periods of unusually rapid growth. Several possibilities are being investigated. Perhaps the first black holes formed from the remnants of very massive stars. Perhaps some formed directly from collapsing clouds of gas under special conditions. Perhaps black hole mergers contributed substantially. None of these possibilities has been established as the universal explanation. They are hypotheses being tested against observations. A third possibility is that the early universe contained galaxies with stellar populations unlike those common today. The first generations of stars formed from material containing far fewer heavy elements. Astronomers sometimes describe such stars as population 3 stars. They have not yet been observed directly with certainty. Their predicted properties remain an important subject of theoretical research. If these stars were especially massive and luminous, even a relatively small population could produce intense radiation. Their short lives could also have enriched surrounding gas with heavier elements, changing the conditions under which later generations of stars formed. If Webb eventually identifies convincing evidence for such a population, it would provide a remarkable window into an era before ordinary stellar chemistry had fully developed. But again, evidence matters. A particular spectral signature may be consistent with metal-poor stars without proving that population 3 stars were responsible. Astronomers must compare several explanations. This distinction between consistency and proof is one of the most important habits in science. A model can explain an observation without being uniquely supported by it. Suppose two different models both reproduce the observed spectrum. The observation alone cannot decide between them. Researchers then search for another measurement that would produce different predictions for the two models. Perhaps another wavelength, perhaps a different emission line, perhaps the abundance of a particular element, perhaps the number of similar galaxies found in a larger survey. This process gradually narrows the possibilities. Webb is particularly valuable because its instruments observe across a broad infrared range. Different wavelengths reveal different physical components. Shorter infrared wavelengths can reveal relatively hot stars and ionized gas. Longer infrared wavelengths can reveal cooler dust and other thermal emission. Together, these observations provide a more complete physical picture, and sometimes the result is less surprising than the first impression. An object that initially appears extraordinarily massive may be reinterpreted after astronomers understand its spectrum. A candidate at extreme redshift may turn out to be closer than initially estimated. A bright source may contain an active black hole. A collection of small galaxies may appear as one blended object in lower resolution observations. These are not failures. They are how astronomy works. The telescope provides increasingly precise evidence, and scientific interpretations evolve with it. Yet the possibility remains that some observations may reveal a genuine tension with existing models. This is where the discussion becomes more profound. The standard cosmological model, often called lambda CDM, describes a universe containing ordinary matter, dark matter, and dark energy, with cold dark matter providing much of the gravitational framework within which galaxies form. The model has been extraordinarily successful. It explains a vast range of observations, from the cosmic microwave background to the distribution of galaxies on enormous scales. But success does not mean completeness. Galaxy formation involves complicated physics occurring on scales that are difficult to calculate from first principles. Gas dynamics, star formation, stellar feedback, black hole activity, and magnetic processes all interact. So a disagreement between a simulation and an observation does not automatically mean that cosmology is wrong. It may mean that galaxy formation is more complicated than the simulation assumes. This is a crucial distinction. The universe can challenge our models without overturning the foundations of physics, and that is precisely why Webb's discoveries are so useful. They provide new tests. If early galaxies repeatedly appear brighter than predicted, astronomers can examine whether star formation efficiency was underestimated. If black holes appear unexpectedly massive, researchers can investigate alternative growth pathways. If galaxy populations appear at redshifts where models predict very few objects, surveys can determine whether the discrepancy is statistically significant. If chemical abundances look unusual, astronomers can examine the history of stellar enrichment. Each possibility creates a different prediction. That is how uncertainty becomes productive. The goal is not to choose the most interesting explanation. It is to discover which explanation survives the evidence, and the evidence is still arriving. The deepest observations are gradually expanding the population of known early galaxies. Spectroscopy is replacing some estimates with more secure measurements. Simulations are becoming more sophisticated. Different telescopes are observing the same objects at different wavelengths. Piece by piece, the early universe is becoming less abstract. But the deeper astronomers look, the more interesting the central question becomes. Perhaps the first galaxies were not as difficult to build as once assumed. Perhaps the early universe was simply more efficient at producing stars. Perhaps black holes played a larger role. Perhaps several processes operated together. Or perhaps the observations will eventually expose something more fundamental that current models have not anticipated. For now, science does not need to choose among these possibilities prematurely. It needs more evidence. And Webb has been built precisely for that purpose. The telescope does not carry a predetermined answer into the darkness. It carries instruments capable of asking better questions. The next step is to follow one of those questions deeper. If an early galaxy really did become luminous remarkably quickly, what would that tell us about the young universe itself? If the earliest galaxies could become luminous faster than astronomers once expected, then something important must have been happening inside the young universe. The question is not whether gravity worked differently. There is no evidence that it did. The more interesting possibility is that familiar processes operated under conditions that were very different from those found in galaxies today. The young universe contained enormous amounts of hydrogen and helium. Heavy elements were scarce. Dark matter had already begun gathering into gravitational structures. Gas was falling into those structures, cooling and becoming concentrated. Then stars appeared. A galaxy does not need to be large by modern standards to contain stars. It needs a region where matter becomes sufficiently concentrated for gravity to overcome the forces resisting collapse. That distinction matters. A small early galaxy could potentially form stars rapidly if conditions favored efficient collapse. And young stars can be extraordinarily luminous. Massive stars burn through their nuclear fuel quickly, producing intense radiation before ending their lives after only a few million years. A population containing many such stars can therefore shine strongly, even if the galaxy itself has not yet accumulated the enormous stellar mass found in mature galaxies today. This gives astronomers one possible explanation for some surprisingly bright early galaxies. Perhaps they were not enormous. Perhaps they were young. The distinction between size, mass, and luminosity becomes essential here. A city filled with bright lamps can appear brilliant from a distance without containing more material than a darker city of the same physical size. In a similar way, a galaxy undergoing an intense burst of star formation can emit enormous amounts of light without necessarily having the same total stellar mass as an older galaxy. But there is another side to this process. Stars do not simply consume their surroundings. They change them. Massive stars release ultraviolet radiation. Their winds push material outward. When some of them die as supernovae, they release energy and heavy elements into the surrounding gas. This process is often called feedback. Feedback can both encourage and suppress future star formation. A supernova can compress nearby gas and help trigger another episode of collapse. But enough explosions can also heat gas and drive it away from a galaxy, reducing the material available to form new stars. In a young galaxy, The balance between these effects may have been particularly important. If feedback was weaker than expected, stars could form rapidly. If feedback was stronger, star formation could be interrupted. The history of a galaxy therefore depends not only on how much matter it contains, but on how that matter interacts with radiation, gravity, turbulence, magnetic fields, and explosions. This is one reason the earliest galaxies are so difficult to model. The fundamental laws are known. The complexity comes from the enormous number of interacting processes. A computer simulation can reproduce gravity across billions of years with remarkable sophistication, but it cannot simply calculate every atom inside every star-forming cloud. Instead, astronomers use physical models and approximations. These models are continually improved by observations. Webb is now supplying observations from an era that was previously accessible only through indirect evidence. That makes the telescope a kind of laboratory for galaxy formation. The laboratory itself is separated from the experiment by billions of light years, but the principle is familiar. Change the conditions, observe the result, compare it with prediction, then revise the model. There is another consequence if early star formation was highly efficient. The first galaxies could have contributed significantly to the process of reionization. The young universe was filled with neutral hydrogen after it cooled sufficiently for atoms to form. Ultraviolet photons from stars could strip electrons from hydrogen atoms, creating ionized regions. As more stars formed, these regions expanded. Eventually, the ionized regions overlapped across much of intergalactic space. The universe became transparent to certain forms of radiation that had previously been strongly absorbed. This transition was not instantaneous. It was a long and uneven process. Some regions may have been ionized earlier than others. Galaxies did not all appear at the same time. Their environments differed. Their radiation output changed as their stellar populations evolved. Webb can help identify the galaxies that existed during this period and measure their properties. But there is a subtle problem. Not every ultraviolet photon produced inside a galaxy necessarily escapes into intergalactic space. Gas and dust can absorb radiation. A galaxy may therefore produce enormous amounts of ionizing radiation while allowing only a fraction to escape. Astronomers describe this with the concept of the escape fraction. The value of that fraction is difficult to measure directly, especially in the distant universe. Yet it matters enormously. If early galaxies were numerous but allowed very little ionizing radiation to escape, they might not have been sufficient to drive reionization. If even relatively small galaxies allowed a substantial fraction of their radiation to escape, their collective contribution could have been much larger. Again, the answer depends on evidence. And this is where one mystery begins to connect with another. The question of how galaxies formed is linked to the question of how the space between galaxies changed. The first stars did not merely illuminate their host systems. They altered the cosmic environment around them. Their radiation travelled outward. Their explosions enriched gas. Their gravity influenced surrounding matter. Their descendants built increasingly complex galaxies. The early universe was becoming a connected system. There is an even more intriguing possibility. The first stars and galaxies may have influenced the formation of black holes. When massive stars die, some can leave behind black holes. If those black holes remain in dense environments containing abundant gas, they can grow. Repeated episodes of accretion can eventually produce much larger black holes. But the enormous masses of some black holes observed when the universe was still young continue to raise difficult questions. How could a black hole grow from a stellar remnant to millions or billions of solar masses in such a short cosmic interval? One possibility is that the initial seeds were larger. Another is that accretion occurred unusually efficiently. Another involves repeated mergers. The real history may include several of these processes. Webb is not primarily a black hole telescope, but its observations can reveal active galactic nuclei in distant galaxies and help determine how common they were. This provides another piece of the puzzle. The early universe may have contained a feedback loop. Stars formed, stars changed their surroundings, black holes grew, black holes released energy. That energy affected gas. The gas then influenced subsequent star formation. Galaxies grew through repeated cycles of interaction. The mature galaxies we see today are therefore not simple structures that appeared fully formed. They are the products of long histories. Webb is allowing astronomers to examine some of the earliest chapters of those histories, and this produces an important change in perspective. When astronomers say that Webb is looking into the past, they do not mean that it is simply searching for the oldest photograph possible. They are reconstructing a physical sequence. First, matter gathered, then gas cooled, stars formed, radiation escaped, elements accumulated, black holes emerged and grew, galaxies assembled, large-scale structures developed. The modern universe emerged from these interconnected processes. The astonishing part is how early some of them had already begun, within a few 100 million years after the Big Bang. The universe was no longer simply a smooth, expanding sea of primordial material. It contained stars, it contained galaxies, it contained complex chemistry, and in at least some places, it contained powerful black holes. Yet there is a danger in describing this too confidently. We have observations of early galaxies. We do not have a complete census of the first galaxies. The objects Webb detects are selected by the sensitivity and wavelength range of the telescope. The faintest systems remain beyond its reach. There may have been enormous populations of small galaxies that Webb cannot easily detect. There may also have been objects whose light is hidden by dust or whose properties are difficult to distinguish from other sources. So the galaxies we see may represent only a portion of the early universe. This is why astronomers continue to push deeper. Every new observation can alter the population statistics. A handful of surprising galaxies can suggest a possibility. A large sample can determine whether that possibility is common, and if the number of early galaxies continues to grow faster than expected, then the question becomes unavoidable. Was the young universe genuinely more efficient at building luminous structures than our models predicted? Or are we still learning how to interpret the light of a galaxy that existed more than 13 billion years ago? The answer will not come from a single photograph. It will emerge slowly from thousands of measurements. And as those measurements accumulate, the story begins to extend beyond galaxies. Because the same infrared sensitivity that allows Webb to see ancient starlight also allows it to peer through dusty regions much closer to home. The telescope built to study the dawn of galaxies can therefore turn its mirror toward another kind of beginning, the birth of stars. And there, among clouds of dust and gas, the history of worlds is already being written. The early universe tells us how the first large structures emerged. But to understand the universe we inhabit today, another story must be followed. The story of stars. Stars are not permanent lights scattered through an unchanging darkness. They are born, evolve, and eventually return material to space. Their lives reshape the environments around them, and the elements they create become part of later generations of stars and planets. Webb was designed to study this process as well. Its infrared vision is particularly valuable inside dense clouds of gas and dust where stars are forming. In visible light, these regions can appear almost opaque. Dust absorbs and scatters shorter wavelengths, blocking our view of the young stars hidden inside. Infrared radiation behaves differently. Longer wavelengths can pass through some of the obscuring material more effectively, allowing telescopes to see structures that remain concealed in visible light. This means Webb can examine two very different cosmic eras with the same basic strategy. It can look backward toward ancient galaxies, and it can look nearby into places where new stars are being born today. The connection between these two investigations is deeper than it first appears. The earliest stars were among the first factories for heavy elements. The young universe began mostly with hydrogen and helium, but modern stars contain much more: carbon, oxygen, neon, magnesium, silicon, iron. These elements were produced through stellar processes and distributed into space. Over generations, enriched gas became the raw material for new stars and planetary systems. The chemistry of planets therefore depends on the history of stars. A rocky world is not made from primordial hydrogen alone. It requires heavier elements, the atoms in Earth's rocks, oceans, atmosphere, and living organisms have passed through a long chain of cosmic processes. This makes star formation more than a beautiful astronomical subject. It is part of the origin story of planetary systems. Webb can examine young stars and the disks of gas and dust that surround them. These disks are important because planets form within them. The process is not observed as a single event. Instead, astronomers study systems at different stages, Some disks contain large quantities of gas and dust. Others show gaps and rings. Some contain structures that may be shaped by newly forming planets. The patterns are clues. A ring in a disk might result from gravitational interactions with an unseen planet. A gap could indicate material being cleared. Complex spirals might reveal gravitational dynamics within the disk. But again, interpretation requires caution. Not every gap proves that a planet is present. Other physical processes can produce similar structures. This is another example of a broader principle in astronomy. The image is the beginning of the investigation, not the end. Webb's instruments can examine the infrared light emitted by dust and molecules within these environments. Spectroscopy can reveal chemical signatures. Certain molecules absorb or emit radiation at characteristic wavelengths. Water vapor, carbon dioxide, methane, and other compounds can leave identifiable patterns under the right conditions. The telescope can therefore investigate not only where material exists, but what that material contains. This becomes especially interesting when the target is a planet outside our solar system. An exoplanet may be too distant to appear as a detailed disk, yet when it passes in front of its star, its atmosphere can alter the star's spectrum slightly. The difference is tiny. The planet may block only a small fraction of the star's light. The atmosphere itself may contribute an even smaller signal. But Webb's sensitivity allows astronomers to measure these subtle changes for selected planets. The resulting spectrum can provide clues about atmospheric composition. This does not mean Webb can immediately determine whether an exoplanet contains life. That conclusion would require much stronger evidence. A molecule associated with biological processes on Earth can also be produced through non-biological chemistry. Atmospheres are complicated systems. Clouds can obscure spectral features. Temperature changes the chemistry. Stellar activity can alter the atmosphere. Ultraviolet radiation can break molecules apart. Chemical reactions can produce the same compounds through very different pathways. So Webb's role is more fundamental. It is building the inventory, before asking whether a distant world is habitable. Astronomers need to know what its atmosphere contains. Before asking how planets become habitable, they need to understand how planetary systems form. Before understanding planetary systems, they need to understand how stars form. And before that, they need the chemistry created by previous generations of stars. The cosmic story is connected. Webb allows astronomers to study several links in that chain. This is one reason the telescope's mission extends far beyond the search for the earliest galaxies. The universe has a history of increasing chemical complexity. At the beginning, the available elements were simple. Stars changed that. Supernovae and stellar winds distributed heavier elements. New stars formed from enriched material. Planets assembled from disks around those stars. Some planets developed atmospheres. Some may have developed conditions suitable for complex chemistry. On at least one world, chemistry eventually became biology. Webb cannot trace that entire chain directly, but it can investigate important stages within it. Consider a stellar nursery. A cloud may contain material destined for many future objects. Some regions collapse into stars. Around some of those stars, disks develop. Within the disks, grains collide and grow. Larger bodies form. Planetesimals emerge. Eventually, planets may appear. This process occurs over millions of years, so Webb cannot watch a single planetary system from beginning to completion. Instead, it observes many systems at different stages. Again, astronomy becomes a reconstruction. Different objects represent different moments in a longer process. And the more systems astronomers observe, the better they can understand which features are common and which are unusual. This is important because our solar system is only one example. For decades, astronomers had only one planetary system to study in detail. Then exoplanet discoveries multiplied the examples. Some systems contain giant planets extremely close to their stars. Some contain multiple planets packed into compact orbits. Some contain small rocky worlds. Some have planets that appear to orbit within regions where temperatures could, under suitable atmospheric conditions, permit liquid water. The diversity is enormous. Webb adds another layer to this diversity by studying atmospheres and the environments in which planets form. The telescope can therefore connect cosmic history at very different scales. A distant galaxy may tell us about the first generations of stars. A nearby stellar nursery may show us how stars are being born today. An exoplanet atmosphere may reveal the chemistry of a world orbiting another star. These subjects might appear unrelated. They are not. They are different chapters in the same physical history. Stars produce elements. Elements become part of planets. Planets orbit stars. Stars form inside galaxies. Galaxies formed from structures that emerged in the early universe. The atoms in a planetary atmosphere can therefore be traced, in principle, through a chain that reaches back toward the first stars. Webb sits somewhere in the middle of that chain. Its mirror collects ancient light from the distant universe. It also collects infrared radiation from nearby clouds of dust. It studies worlds that formed around other stars, and in each case, the same basic instrument is doing something remarkably simple. It is collecting photons. Those photons carry different histories. Some began their journey billions of years ago in a young galaxy. Others were emitted yesterday, in cosmic terms, by warm dust around a newborn star. Still others passed through the atmosphere of a distant planet before reaching the telescope. Webb does not need to travel to those places. The information travels to Webb. That is perhaps the most elegant feature of astronomy. The universe is constantly sending evidence outward. Light crosses the darkness. Telescopes wait, and when the photons arrive, they allow us to reconstruct events that occurred long before anyone was present to witness them. But the deeper Webb looks into these connected histories, the more another mystery appears. If stars, galaxies, planets, and chemistry are all linked through cosmic evolution, then where exactly did the first significant complexity begin? Was it inside the first stars, inside the first galaxies, or was the process already encoded in the structure of the universe before the first stars ever existed? To approach that question, Webb must return to the deepest part of its mission, the cosmic dawn. The history of the universe can be divided into chapters, but nature does not recognize the boundaries between them. The first stars belong to the story of the first galaxies. The first galaxies belong to the story of cosmic reionization. The elements created inside stars belong to the story of planets. And the planets that form around later generations of stars belong to a history that ultimately reaches back toward the earlier structures of the cosmos. Webb's observations begin to reveal these connections more clearly. One of the most important is the relationship between galaxies and the black holes at their centers. In the modern universe, many large galaxies contain supermassive black holes. The Milky Way, for example, contains Sagittarius A, a black hole with a mass of roughly 4 million suns. The black hole itself is dark. What can become extraordinarily bright is the material surrounding it. Gas falling toward a black hole can form a rapidly rotating accretion disk. Friction and gravitational effects heat this material to enormous temperatures, producing radiation across a wide range of wavelengths from far away. The glow of an active black hole can therefore outshine the stars in its host galaxy. This creates an unexpected connection. The same distant galaxy that astronomers want to use as a record of early star formation may also contain a rapidly growing black hole whose radiation changes the entire appearance of the system. In some cases, the black hole may even help explain why a galaxy appears unusually luminous, but the relationship may work in both directions. Black holes can influence their host galaxies. Powerful outflows from active galactic nuclei can inject energy into surrounding gas. That energy can heat or push away material that might otherwise form stars. Black hole activity may therefore suppress star formation under some circumstances. Yet other interactions can compress gas and potentially encourage star formation. The balance is complicated. Galaxies and black holes appear to evolve together, but the exact relationship remains an active area of research. This connection becomes especially interesting in the early universe. If massive black holes already existed when the cosmos was only a few 100 million years old, then their origins must have been remarkably early. A black hole formed from the death of a massive star begins with perhaps tens of solar masses, depending on the star and the details of its evolution. Reaching millions or billions of solar masses requires enormous growth. That growth takes time, unless the original seed was unusually massive. The black hole accreted material at very high rates, experienced repeated mergers, or some combination of these processes occurred. Webb can observe some of these early active black holes. Its observations do not automatically tell us how their seeds formed, but they can reveal when such objects existed and what their environments looked like. That allows astronomers to constrain possible histories. The same logic appears elsewhere. Consider the chemistry of a young galaxy. If astronomers detect strong signatures of elements such as oxygen, carbon, or other heavy elements in a galaxy from an early epoch, those elements must have been produced by earlier generations of stars. The presence of metals therefore becomes a kind of clock. It does not provide an exact timestamp, but it tells us that stellar evolution had already been underway. Stars had already formed, some had already died. Their material had already been returned to surrounding gas. New stars had then formed from that enriched material. The chemical history of a galaxy therefore records its stellar history. This is one of the subtle strengths of infrared spectroscopy. A distant galaxy may look like a small, faint point of light. Its spectrum can reveal a history spanning multiple generations of stars. The photons arriving at Webb have travelled billions of years, but they can still carry information about chemical processes that occurred inside stars. In this sense, light preserves more than appearance. It preserves traces of physical history. Another connection emerges when astronomers compare galaxies across cosmic time. Modern galaxies often contain mature structures. Some have enormous stellar disks, some have central bulges, some contain large populations of older stars. Others are dominated by ongoing star formation. But the earliest galaxies tend to be smaller and more irregular. This suggests that galaxies grew over time. They merged, they accreted gas, they formed stars, they interacted with their environments. Yet the process may have been more chaotic than a simple picture of gradual growth suggests. Small galaxies could collide, gas could be compressed, star formation could surge, black holes could become active, outflows could remove gas, then the system could settle before another interaction disturbed it. The galaxy we see today is therefore the result of countless interactions. Webb gives astronomers an opportunity to observe those processes closer to their beginnings. This has consequences for our understanding of the Milky Way. Our galaxy is not an isolated structure that appeared fully formed. It also has a history. Astronomers believe the Milky Way grew through the accumulation and merger of smaller systems. Some ancient stellar populations in the Milky Way may preserve evidence of those events. The distant galaxies observed by Webb provide a complementary view. Instead of examining the archaeological remains of our own galaxy, astronomers can look directly at other galaxies while they are still undergoing the kinds of processes that helped shape galaxies like ours. The two approaches meet. Nearby evidence tells us about our galaxy's past. Distant observations show how galaxies at comparable stages may have behaved. This is one reason looking outward can also mean looking inward. The deeper Webb looks into space, the more it helps explain our own cosmic surroundings. There is another unexpected connection. The first galaxies were not merely building blocks of larger galaxies. They were also sources of radiation that changed the intergalactic medium. Their ultraviolet light contributed to ionization. That process changed how radiation traveled through space, so the properties of early galaxies influenced the environment in which later galaxies developed. The universe was not simply a collection of independent objects. It was an interconnected system. A galaxy could change its surroundings. Those surroundings could influence other galaxies. Gas could move between systems. Heavy elements could spread into intergalactic space. Radiation could travel across enormous distances. Over billions of years, these interactions gradually produced the large-scale universe we see today. And yet one of the most interesting consequences of Webb is that it allows astronomers to connect the very large with the very small. A galaxy may span tens of thousands of light years. Inside it are stars. Inside stars are nuclear reactions. Those reactions create elements. Those elements form grains of dust. Dust becomes part of planetary disks. Planets develop atmospheres. Atmospheres interact with radiation. A spectrum from a distant world can therefore contain information connected through a long chain of physical processes to stellar and galactic evolution. The telescope's mission is not divided into completely separate subjects. It is studying a network. Cosmic history flows from one scale into another. This becomes particularly clear when Webb observes molecules. Molecules in space can form within cold clouds of gas and dust. Some survive inside disks around young stars. Others become part of planets. Astronomers can identify molecular signatures through spectroscopy, allowing them to investigate chemical inventories in places far beyond our solar system. The chemistry of a planetary system may therefore provide clues about the environment from which it formed. Was the system rich in carbon? Was water present? Were complex molecules available? How did radiation from the young star affect them? None of these measurements provides a direct path to life, but they help establish the chemical context in which planets develop. The connection is subtle. Cosmology leads to galaxies. Galaxies lead to stars. Stars create elements. Elements form planets. Planets develop atmospheres. And atmospheres become observable through the light of distant stars. A telescope designed to study the early universe can therefore end up investigating questions about worlds that did not exist when the earliest galaxies were forming. This is not a contradiction. It is the consequence of cosmic evolution. The same laws of physics operate across these enormous spans of time. Webb is exploiting that continuity. But there is one more connection that may be even more important. Every observation of an ancient galaxy is also an observation of the universe, under conditions that no longer exist. We cannot recreate the first galaxies in a laboratory. We cannot travel backward to the cosmic dawn. We can only receive the surviving light. That means Webb is not simply exploring distant space. It is sampling different moments in the history of reality itself, and if those moments can be connected into a coherent sequence, then the telescope may help answer a question larger than how galaxies formed. It may help explain how a nearly primordial universe developed the complexity we see around us. Yet complexity creates its own mystery. The farther we trace the chain backward, the closer we come to the point where the familiar structures of stars and galaxies disappear. Beyond that boundary lies the beginning of cosmic history that Webb is capable of probing only indirectly. And to understand what Webb is finding there, we need to examine what modern astronomy is actually seeing now. Not what the telescope was expected to discover, not what early models predicted, but what the observations themselves are beginning to reveal. By the time the James Webb Space Telescope had completed its early years of science operations, something became increasingly clear. The telescope was not simply confirming the universe astronomers expected to find. It was revealing a universe with more variety, more complexity, and sometimes more uncertainty than earlier observations had suggested. That does not mean the foundations of modern cosmology had collapsed. They had not. Instead, Webb was doing something more useful. It was forcing astronomers to examine the details, and details are where scientific understanding often changes. One of the most important areas has been the early universe. Webb has now confirmed galaxies from remarkably early times, including observations of galaxies that existed only a few 100 million years after the Big Bang. In January 2026, astronomers reported a confirmed galaxy known as Moye D4 seen when the universe was about 280 million years old. That number is difficult to appreciate. The universe is approximately 13.8 billion years old. A galaxy seen 280 million years after the beginning existed during a period when the cosmos was still extraordinarily young. Yet it was already producing enough light for a telescope near Earth to detect. This does not mean the galaxy was already mature in the modern sense. It means that the physical processes capable of producing stars and galaxies had become active remarkably early. Webb has also found objects whose properties are difficult to fit neatly into the simplest expectations of early galaxy formation. One example is the population informally known as the little red dots. These compact reddish sources became an unexpected feature of Webb surveys. Their exact nature remains under investigation, but observations increasingly suggest that at least some contain rapidly growing black holes. The mystery is particularly interesting because these objects may represent a previously underappreciated phase of galaxy and black hole evolution. In late 2025, Webb observations confirmed an actively growing supermassive black hole in a galaxy seen only about 570 million years after the Big Bang. Then, in 2026, another observation pushed the question further. Researchers studied a distant little red dot in the galaxy cluster Abell 2744. By mapping the motion and composition of gas around its central black hole, they obtained evidence suggesting that the roughly 50 million solar mass black hole may have existed before its host galaxy became comparably massive. The result does not mean astronomers have discovered the definitive origin of all supermassive black holes. It does something more important. It gives them a new constraint. If some black holes were already enormous before their host galaxies had grown substantially, then at least some black hole seeds may have started much larger than the remnants of ordinary stars. One possibility involves the direct collapse of very large concentrations of gas. Another involves unusual pathways of rapid growth. The exact history remains uncertain, but the observation changes which possibilities deserve serious attention. Webb has also found unexpected evidence about the earliest galaxies in another way. A galaxy known as JD's GSCZ31 has been observed at a time only about 330 million years after the Big Bang. Its spectrum contains unexpectedly strong Lyman alpha emission, a signature of hydrogen that is difficult to observe through the neutral hydrogen fog expected to surround the early universe. This creates another question. If the surrounding universe was still substantially filled with neutral hydrogen, how did this particular ultraviolet light escape? Perhaps the galaxy had already created a local bubble of ionized gas. Perhaps its environment was unusual. Perhaps the process of reionization was more patchy and locally structured than a simple timeline suggests. The observation does not provide a final answer, but it turns an abstract question into something measurable. The early universe was not uniformly changing everywhere at the same rate. It may have contained islands of intense activity surrounded by regions that remained comparatively dark. Webb is beginning to reveal those islands, and its discoveries are not restricted to distant galaxies. The same telescope has become an extraordinarily sensitive laboratory for planetary systems. In 2025, Webb observations of the young HR 8799 system detected carbon dioxide in the atmospheres of its directly imaged giant planets. The measurements provided evidence consistent with those planets having formed through a process resembling the formation of Jupiter and Saturn, in which solid cores accumulated material and subsequently attracted large quantities of gas. Here again, Webb is not merely taking a photograph. It is reading chemistry. Carbon dioxide is not interesting because its name sounds familiar. It is interesting because chemical abundances can reveal something about planetary formation. A planet's atmosphere is partly a record of where and how that planet formed. The composition of the surrounding disk matters. The temperature matters. The amount of solid material matters. The planet's subsequent evolution matters. By measuring atmospheric chemistry, astronomers can therefore begin reconstructing the history of worlds around other stars. And in July 2026, Webb provided another example of how indirect evidence can reveal something hidden. Astronomers identified a third giant planet in the Beta Pictoris system, called Beta Pictoris d. Unlike the previously known planets in the system, it was identified through the chemical fingerprint of its atmosphere rather than simply by finding a bright point of light. The observation illustrates an important transformation in exoplanet astronomy. The goal is no longer simply to discover planets. Astronomers are increasingly trying to characterize them. That means asking what their atmospheres contain, how hot they are, how clouds behave, how their chemistry changes with altitude, how their atmospheres interact with radiation from their stars, and eventually, under favorable circumstances, whether any combination of atmospheric properties could indicate an environment of particular biological interest. But caution remains essential. A chemical molecule is not the same thing as evidence of life. The same molecule can often be produced through multiple physical or chemical pathways. An atmosphere is a system, not a list of ingredients. To understand it, astronomers need multiple measurements and models. This is why Webb's contribution is so valuable. It expands the number of worlds for which meaningful atmospheric information can be obtained. It turns distant planets into objects of comparative science. There is a similar transformation happening in the study of stars. Webb's infrared vision can penetrate clouds of dust surrounding young stellar systems. In 2026, observations of the FS Tau region revealed numerous protostars hidden within dense material, including very young objects only around 1 to 3 million years old. These objects provide snapshots of stellar infancy. They cannot be followed continuously from birth to maturity, because stellar formation unfolds over millions of years. Instead, astronomers observe many systems at different stages. Some are deeply embedded in dust. Some are beginning to clear their surroundings. Some have developed disks, some display jets, together. These systems allow researchers to reconstruct the sequence. The pattern is similar to the study of early galaxies. Different objects provide different moments in a longer physical process. The telescope is therefore functioning across several kinds of cosmic history at once. It observes the birth of stars. It studies planetary atmospheres. It examines mature galaxies. It searches for the earliest luminous structures. It investigates black hole growth. These subjects appear unrelated until the scale is widened. Stars form inside galaxies. Galaxies contain black holes. Stars create elements. Those elements become part of planetary systems. Planets inherit chemistry from the environments in which their stars formed. And all of these structures emerged within the expanding universe. Webb's observations therefore form a web of evidence rather than a single story. One discovery can influence another. A better understanding of early galaxies can improve models of star formation. Better models of stars can improve estimates of the chemical enrichment of galaxies. Better knowledge of black hole growth can change our understanding of early galaxy evolution. Better atmospheric measurements can reveal how planetary systems develop. And better observations of distant galaxies can test the larger cosmological framework in which all of these processes occur. This is what modern astronomy increasingly looks like. Not one telescope answering one question. Many instruments examining the same universe from different angles. Webb's infrared observations can be compared with Hubble's visible and ultraviolet measurements. Ground-based observatories can provide complementary spectra. Radio telescopes can trace cold gas. X-ray observatories can reveal energetic black holes. Computer simulations can construct theoretical universes against which observations are tested. The strength comes from comparison, and the comparison is beginning to reveal something profound. The universe is more interconnected than the categories we use to study it. A distant galaxy is not merely a distant galaxy. It is a laboratory for star formation. A star is not merely a ball of plasma. It is a chemical factory. A planet is not merely a world orbiting another star. Its atmosphere can preserve clues about the disk from which it formed. A black hole is not merely an object that consumes matter. Its growth can influence the evolution of an entire galaxy. Webb is helping astronomers see these connections. Yet with every new connection comes another boundary. There are still questions the telescope cannot answer. There are objects too faint to detect. There are chemical signatures too ambiguous to interpret uniquely. There are galaxies whose distances remain uncertain until spectroscopy confirms them. There are early black holes whose origins remain unresolved. And there are entire periods of cosmic history that remain only partially observed. The telescope has expanded the frontier. It has not removed the frontier. In fact, it may have made that boundary more interesting, because the more clearly astronomers see the early universe, the more precisely they can identify what they still do not understand. And that is where the next part of the story begins. Not with what Webb has discovered, but with what its discovery still cannot tell us, for all that the James Webb Space Telescope has revealed. Some of the most important questions remain unanswered. This is not a failure of the telescope. It is one of the clearest signs that an instrument has reached a genuinely interesting frontier. Every new observation reduces some uncertainties while exposing others. The first galaxies are no longer entirely theoretical. We can detect them. We can measure their redshifts. We can study their spectra. We can estimate their stellar populations and rates of star formation. We can investigate the black holes that existed within some of them. Yet the earliest chapters remain incomplete. We still do not know exactly when the first stars formed. We do not know precisely how the first galaxies assembled. We do not know which kinds of objects contributed most strongly to reionization. And we do not know exactly how the first massive black holes acquired their enormous masses. These questions are connected, but each contains uncertainties of its own. Consider the first stars. Astronomers expect them to have formed from gas containing almost no elements heavier than helium, because heavier elements influence how gas cools, fragments, and collapses. The first stars may have formed differently from later generations. Models often predict that some of the earliest stars were very massive, but prediction is not observation. Despite years of searching, astronomers have not yet obtained an unambiguous direct observation of a population of pristine population 3 stars. The difficulty is partly distance. The first stars were extraordinarily far away. They were also short-lived. A massive star may survive for only a few million years, which is a brief interval compared with the billions of years of cosmic history that followed. The light from such a star can therefore be faint, red-shifted, and mixed with the radiation of other stars in its surrounding galaxy. Even if Webb detects a galaxy containing extremely metal-poor stars, proving that those stars belong to the very first generation requires careful chemical analysis. The evidence must distinguish pristine stars from later stars that simply formed from unusually unenriched gas. This is an example of a recurring problem. The universe does not label its historical artifacts for us. Astronomers have to infer their origins. The same uncertainty applies to the first galaxies. A galaxy observed at a very high redshift existed early. That is a fact. But what happened inside it is an interpretation based on measurements. Its stellar mass is inferred. Its age distribution is modelled. Its star formation history is reconstructed. Its dust content is estimated. Its black hole activity may be separated from its stellar light through spectral modelling. Every additional inference introduces another layer of uncertainty. This does not make the conclusions meaningless. It means they have different levels of confidence. A measured wavelength is not equivalent to an estimated stellar mass. A detected emission line is not equivalent to a complete chemical history. A model that fits the data is not automatically the unique explanation. Science depends on keeping these distinctions visible. This becomes particularly important when astronomers compare Webb's observations with computer simulations. A simulation may predict how many galaxies should exist above a certain brightness at a particular redshift. Webb then measures the actual population. If the numbers agree, confidence in the model increases. If they differ, scientists investigate the source of the discrepancy. But there are many possible sources. Perhaps the cosmological model is incomplete. Perhaps the simulation's treatment of star formation is inaccurate. Perhaps stellar populations are more luminous than assumed. Perhaps dust has been modelled incorrectly. Perhaps the survey has observational biases. Perhaps a small sample contains an unusually bright group of objects. The difference between these possibilities can be enormous. A disagreement with the simulation, therefore, does not immediately mean that the standard model of cosmology has failed. It means the model has encountered something worth understanding. This is especially important because the standard cosmological framework has survived many independent tests. The cosmic microwave background provides a detailed record of the early universe. Large-scale galaxy surveys reveal the distribution of matter. Gravitational lensing traces mass. The expansion history can be measured through several independent methods. Together, these observations form a remarkably coherent picture. The challenge from Webb is therefore more subtle. It is testing the details of how that broad cosmological framework produces galaxies. The difference matters. A model can correctly describe the large-scale structure of the universe, while still containing incomplete descriptions of how stars form inside individual galaxies. The laws of gravity may be working perfectly while the astrophysics of gas remains difficult to calculate. This is why the earliest galaxies are such valuable laboratories. They existed under conditions that cannot be reproduced locally. The universe was younger. Gas was less chemically enriched. Dark matter structures were smaller. The radiation background was different. Black holes were growing within environments unlike most galaxies today. Webb provides a way to observe those conditions indirectly through their surviving light. But there is another unanswered question. How did reionization actually happen? Astronomers know that the intergalactic medium transitioned from predominantly neutral hydrogen to predominantly ionized hydrogen. They also have independent evidence that this transition occurred during the first billion years of cosmic history. What remains uncertain is the detailed sequence. Was the process dominated by numerous small galaxies? Did larger galaxies contribute most of the ionizing radiation? Did active black holes play a significant role? How much radiation escaped from galaxies into intergalactic space? Was reionization relatively smooth? Or did it proceed through irregular bubbles and patches? The universe may have been filled with expanding regions of ionized gas surrounding early sources of radiation. If so, the geometry of those regions would have depended on the distribution and activity of the first galaxies. Webb can identify some of those sources. But identifying the sources is not the same as measuring their total contribution. The photons capable of ionizing hydrogen are mostly emitted at ultraviolet wavelengths. Much of that radiation may be absorbed before it escapes the galaxy. The amount that gets out is therefore critical, and that quantity can be difficult to determine for the most distant systems. Another mystery concerns black holes. Some massive black holes clearly existed surprisingly early, but their origins remain uncertain. If they began as ordinary stellar remnants, they had to grow rapidly. If they began as larger seeds created by the direct collapse of gas, astronomers need to understand which environments allowed that process. If mergers played an important role, the young universe must have provided sufficiently dense environments for repeated encounters. There may not be one universal pathway. Different black holes may have followed different histories. This is another lesson emerging from Webb. The universe does not have to choose one mechanism. Several mechanisms can operate simultaneously. A galaxy may contain rapidly forming stars and a growing black hole. Its gas may be enriched by supernovae while also being expelled by stellar winds. Its black hole may inject energy into the surrounding environment. Its neighboring galaxies may merge with it. Cosmic evolution is not a sequence of isolated events. It is an interaction of processes, and interactions are difficult to reconstruct from light alone. There is yet another limitation. Webb observes the universe through electromagnetic radiation. That is enormously powerful. But it is not the only way information travels through the cosmos. Gravitational waves can carry information about merging black holes and neutron stars. Neutrinos can escape environments from which light may struggle to emerge. Cosmic rays reveal energetic processes that electromagnetic observations alone cannot fully describe. Webb therefore occupies one part of a much larger astronomical network. To understand the deepest cosmic questions, astronomers increasingly combine observations from many kinds of instruments. The future of astronomy will not be defined by one telescope. It will be defined by how different measurements fit together. This brings us to a quiet but important realization. The limits of Webb are not simply technical. They are also conceptual. Even with perfect observations, some questions cannot be answered by a telescope alone. Knowing that a molecule exists does not automatically reveal how it formed. Knowing that a black hole is massive does not reveal its complete origin. Knowing that a galaxy existed early does not tell us every step by which it assembled. The data must be interpreted through physical models, and those models must remain open to revision. This is why unanswered questions are not empty spaces in scientific knowledge. They are boundaries. They mark the places where observation, theory, and inference meet. Webb has pushed those boundaries outward. It has brought the cosmic dawn closer to observation. It has exposed young galaxies, young stars, growing black holes, planetary atmospheres, and chemical environments that earlier instruments could barely detect. But the telescope has not transformed the universe into a completely solved problem. Quite the opposite. The ancient cosmos now contains more measurable detail than ever before. And because there is more detail, there are more places where our explanations can be tested. Beyond those explanations lies the true frontier. Not simply seeing farther, but understanding what the light means. And that is where astronomy becomes most difficult. Because eventually, the photons stop providing enough information to distinguish one possibility from another. At that boundary, the telescope has done its work. The remaining question belongs to us. What can we legitimately conclude from the evidence we have? And how much of the ancient universe is still hidden inside the evidence we have not yet learned how to interpret? There is a boundary in astronomy that cannot be marked on a map. It is not a particular distance. It is not a specific redshift. It is the point where the available light becomes too faint, too altered, or too ambiguous to tell us confidently what produced it. The James Webb Space Telescope has moved that boundary, but it has not removed it. Beyond the galaxies Webb can detect, there are almost certainly smaller and fainter systems. Beyond those are the first stellar groups. Beyond those lies an era when the universe contained no stars at all. The telescope can approach that history. It cannot simply cross it. One reason is sensitivity. Even with its enormous mirror, Webb can collect only the photons that actually reach its detectors. A distant galaxy may emit an extraordinary amount of radiation, yet almost none of those photons may arrive at Earth. Cosmic expansion spreads the radiation over enormous distances. The signal becomes weaker. At the same time, the wavelengths shift. The object can become increasingly difficult to distinguish from the background. This creates a practical limit. Longer observations can collect more photons, but telescope time is finite. Astronomers must decide which observations provide the greatest scientific return. A few very deep observations may reveal extraordinary individual objects. Wider surveys may reveal thousands of ordinary ones. Both are valuable. The first can expose unusual physics. The second can determine whether unusual objects are genuinely unusual. This tension between depth and breadth exists throughout astronomy. Webb can stare deeply into a tiny region of sky, or it can distribute observing time across larger areas. The choice depends on the scientific question. If astronomers want to identify the faintest possible galaxies, depth is essential. If they want to determine how common those galaxies are, area becomes equally important. The frontier therefore depends not only on what the telescope can detect, but on how researchers use its limited time. There is also the problem of cosmic foregrounds. The universe between galaxies is not completely empty. Dust within the Milky Way can obscure distant sources. Stars within our own galaxy can appear in the foreground. Diffuse infrared emission can contribute background radiation. Other galaxies can overlap in the same line of sight. At extreme distances, several faint sources can become difficult to separate. Webb's high resolution helps, but even the most sophisticated instrument must contend with the geometry of the universe. Sometimes two unrelated objects simply happen to lie along nearly the same line of sight. Another difficulty comes from gravitational lensing. A massive galaxy cluster can bend light passing around it. This can magnify distant galaxies, making objects visible that would otherwise be too faint. Gravitational lensing is extraordinarily useful. It acts like a natural telescope placed in space, but it also distorts the image. A distant galaxy can appear stretched, duplicated, or magnified. Astronomers must model the mass distribution of the foreground cluster to reconstruct the original source. The technique therefore provides both an advantage and a complication. The universe itself can help us see farther. It can also make what we see harder to interpret. The same principle appears when studying extremely distant galaxies. Their light may have travelled through regions containing gas and dust. Some wavelengths can be absorbed, others can be scattered. The final spectrum is therefore not always a perfect record of the source. It is the source after billions of years of interaction with its environment. Astronomers must reconstruct the original signal. This is one reason the frontier of astronomy is not simply technological. It is analytical. More sensitive detectors produce more data. More data require more sophisticated models. And more sophisticated models reveal more ways in which an apparently simple observation can have multiple interpretations. There is also a fundamental limit imposed by cosmic history itself. Webb observes infrared light, but the earliest universe contained a period before stars existed. During that era, there were no galaxies shining in ordinary starlight. There was no stellar ultraviolet radiation. There were no supernovae. There were no mature planetary systems. There was matter and radiation evolving according to the conditions of the young cosmos. Webb cannot simply photograph that darkness. The telescope's deepest mission is therefore not to see the first instant of the universe. It is to approach the first luminous structures. This distinction is essential. The Big Bang was not an explosion occurring at one point in an otherwise empty space. The early universe was hot and dense everywhere. As it expanded, it cooled. Atoms eventually formed. The cosmic microwave background was released roughly 380,000 years after the beginning. Then came a long period often called the Cosmic Dark Ages. Only later did the first stars ignite. Webb operates primarily on the far side of that transition. It investigates what happened after the universe became capable of producing its first lights. But even this frontier contains an additional complication. The light from the first stars may be mixed together. A telescope may not be able to isolate individual primordial stars. Instead, it may observe their combined radiation within a small galaxy or stellar cluster. This means the signatures of the first stars may need to be inferred statistically. Astronomers may search for unusual chemical abundances. They may look for spectral patterns predicted by metal-poor stellar populations. They may examine the absence of certain elements. They may compare multiple galaxies. The evidence may never take the form of a single unmistakable image. It may emerge from a pattern across many observations. This is how much of modern astronomy progresses. The most important discoveries are often not obvious in a single photograph. They emerge after data are compared across time, wavelength, and location. The frontier is therefore a moving target. As Webb detects fainter galaxies, the threshold shifts. As spectroscopic techniques improve, some uncertain distances become secure. As simulations become more sophisticated, previous disagreements may become understandable. Then new discrepancies appear. The edge of knowledge keeps moving because every answer changes the question. This is particularly visible in cosmology. For decades, astronomers had only a rough understanding of the earliest galaxies. Then increasingly sensitive telescopes began detecting them. Now Webb is finding galaxies at even earlier times. The result is not that the universe suddenly became mysterious. It is that the mystery has become more precise. We now know where some galaxies were. We can estimate when they existed. We can measure their spectra. We can examine their environments. And therefore we can ask much more specific questions. How massive were their stars? How quickly did they form? How much radiation escaped? How did black holes grow? How much heavy element enrichment had already occurred? How did these systems influence the surrounding intergalactic gas? These are questions that can be tested. That is an important difference between scientific mystery and speculation. A scientific mystery is connected to measurable evidence. It has competing explanations. Those explanations make predictions. Future observations can distinguish among them. Webb therefore occupies an unusual position. It is powerful enough to reveal phenomena that were previously inaccessible, but it is not powerful enough to answer every question those phenomena create. That tension is productive. Consider the possibility that the earliest galaxies were smaller than expected but formed stars very efficiently. Future observations could test how common such systems were, if they are widespread. Models of early star formation may need adjustment. If they are rare, the apparently surprising observations may represent an unusual population. Likewise, if massive black holes are found repeatedly at very early times, their formation models will need to account for that population. If they are rare, unusual formation pathways may be sufficient. The distinction depends on statistics. This is why the frontier is not necessarily a single object at the edge of visibility. It is the boundary between what can be measured and what can be inferred. Webb can reveal an ancient galaxy, but the history of that galaxy is partly hidden. It can reveal an exoplanet atmosphere, but the origin of every molecule may remain uncertain. It can detect a black hole, but its original seed may be invisible. It can observe the consequences of cosmic evolution. It cannot rewind the universe and watch the events happen again. There is no second experiment, only surviving evidence, and yet that evidence is extraordinary. A photon collected by Webb may have travelled for more than 13 billion years. It crossed expanding space. It passed through environments that no longer exist. It survived while stars were born and died. It travelled while galaxies merged. It continued through the formation of the solar system, and eventually, it reached a telescope assembled on Earth and unfolded in space. That single photon cannot tell us everything, but billions of photons, measured carefully, can reveal an astonishing amount. The frontier, therefore, does not end where the telescope stops seeing. It continues into the interpretation of what it sees, and beyond that lies a deeper question. If the earliest galaxies can be observed, and if their histories can be reconstructed, how far can this method eventually take us toward understanding the origin of cosmic structure itself? There is a quiet shift that happens when astronomy moves from discovering distant objects to understanding their history. At first, the universe appears to be a collection of separate things: stars, galaxies, nebulae, black holes, planets. But the deeper we look, the harder it becomes to keep these categories apart. They are connected by time. A star is born from material that came from earlier stars. A planet forms from material surrounding a young star. A galaxy grows through the accumulation of gas and smaller galaxies. A black hole can influence the evolution of the galaxy around it. And all of these structures emerge from a universe whose earliest conditions were vastly simpler than the environment we see today. The James Webb Space Telescope is helping astronomers trace these connections. This changes the meaning of cosmic origins. The origin of the universe is not simply the origin of space and time. It is also the beginning of a long process through which complexity emerged. At the earliest observable stages, the universe was dominated by hydrogen and helium. There were no rocky planets, no oceans, no trees, no biological chemistry, no stars like the Sun, no galaxies like the Milky Way. Yet within the laws of physics already operating in that young cosmos were the processes that could eventually produce all of them. Gravity gathered matter. Matter collapsed. Stars ignited. Nuclear reactions created heavier elements. Those elements escaped into space. New generations of stars formed. Around some of those stars, disks of dust and gas assembled into planets. The sequence took billions of years, but the ingredients were gradually transformed. Webb allows astronomers to observe several stages of that transformation. This gives the telescope an unusual scientific role. It is not simply looking farther than previous observatories. It is looking at different moments in the same long process. The distant early galaxy and the nearby stellar nursery are separated by billions of years, but the physics connecting them is continuous. The gas in a young galaxy becomes the raw material for stars. Stars enrich that gas. Enriched gas becomes part of later galaxies. Those galaxies produce new stars. Some of those stars develop planetary systems. The same elements that were absent in the earliest generations eventually become abundant enough to build worlds. This means that cosmic history can also be understood as a history of increasing chemical diversity. The first stars did not create every element in the periodic table. Some elements require particular stellar processes. Some are produced in supernovae. Others arise in neutron star mergers or other extreme environments. The chemical inventory of the universe is therefore the result of many generations and many kinds of cosmic events. Webb can examine some of the products of these processes in distant galaxies. It can identify spectral signatures associated with elements and molecules. These measurements allow astronomers to ask when different forms of chemical enrichment became common. That question matters because planets require heavy elements. The early universe could not easily build a rocky planet from hydrogen and helium alone. It needed previous generations of stars. This creates an important temporal relationship. There was a period when the universe was too chemically primitive for planetary systems resembling ours to be common. Then stars began enriching their surroundings. Eventually, planets became possible in increasing numbers. So when we ask when planets could have formed, we're also asking when stars had already lived and died. Planetary history therefore depends on stellar history, and stellar history depends on galactic history. The chain reaches backward, but Webb also helps reveal something else. The universe did not become complex in a smooth, predictable progression. There were bursts, mergers, collisions, periods of intense star formation, periods when black holes became extremely active, regions where gas accumulated, regions where gas was expelled. The history of the cosmos is dynamic. This matters when thinking about our own existence. Earth can appear isolated because its surface is so different from the vacuum of interstellar space. But physically, Earth is made from material that once belonged to stars. The oxygen in Earth's atmosphere was created through stellar processes. The carbon in living organisms was produced inside stars. The silicon in rocks and the iron in Earth's core are products of cosmic nucleosynthesis. This does not make life inevitable. It does not imply that the universe was designed to produce life. It simply means that the chemistry required for complex worlds emerged through ordinary physical processes operating over enormous stretches of time. Webb's observations allow astronomers to investigate how widespread those ingredients are. And that introduces one of the most fascinating questions in modern astronomy. How unusual is the chemical history that produced Earth? We now know that planets are common. Thousands of exoplanets have been confirmed, and the population continues to expand. But knowing that planets are common is different from knowing that Earth-like conditions are common. A planet's distance from its star is only one factor. Atmospheric composition matters. Pressure matters. Temperature matters. Clouds matter. Stellar radiation matters. Magnetic fields may matter. Geological processes matter. The history of water matters. The stability of the planetary environment matters. Webb can investigate some of these properties, particularly atmospheric chemistry, but it cannot independently determine whether a planet is alive. That boundary is scientifically important. Suppose astronomers detect a molecule that, on Earth, is strongly associated with biological activity. That would be interesting, but it would not automatically constitute evidence of extraterrestrial life. Chemistry does not belong exclusively to biology. Molecules can be produced through photochemical reactions, geological processes, atmospheric interactions, and other non-biological pathways. A convincing case for life would require multiple lines of evidence that could not be easily explained by known abiotic processes. Webb therefore contributes to the search by narrowing possibilities. It tells us what is present. It tells us what is absent. It reveals which atmospheres are chemically active. It shows us which planets have clouds, hazes, or unusual thermal structures. The telescope builds the physical context from which stronger questions can eventually be asked. This approach reflects a broader principle. Science becomes more powerful when it resists the temptation to make observations say more than they actually do. A distant planet with water vapor is a planet with water vapor. It is not automatically a second Earth. A distant galaxy with an enormous black hole is evidence for an early massive black hole. It is not automatically evidence that our understanding of gravity is wrong. A bright galaxy at extreme redshift is evidence of early luminous structure. It is not automatically evidence that the standard cosmological model has failed. The importance of Webb lies partly in this discipline. It gives scientists better measurements. Better measurements create better constraints. Better constraints eliminate some explanations while strengthening others. Over time, the remaining possibilities become narrower. This is how our understanding of reality advances, not through one perfect observation, through a long accumulation of evidence. There is also a philosophical consequence. For centuries, human beings have tended to think of the present as the primary reality, and the past as something that disappeared. Astronomy complicates that intuition. The past has not completely disappeared. It survives in light. A galaxy that existed billions of years ago may no longer look exactly the same. Its stars may have died. Its structure may have changed. It may have merged into another galaxy. But the light it emitted during that earlier stage is still travelling through space. Webb receives some of that ancient information. In this sense, cosmic history is not entirely gone. It is distributed across the universe in radiation. The telescope gathers a tiny fraction of it. This also changes the way we think about distance. A distant galaxy is not merely a location far away. It is a record. The farther the galaxy, the earlier the record. The sky becomes a kind of layered archive in which different distances correspond to different epochs. Webb is extending our access to that archive. But an archive is useful only if its records can be interpreted. And that brings us back to uncertainty. The universe does not provide labels saying which process created each photon. Astronomers reconstruct the story through physics. They compare observations with models. They search for independent evidence. They test predictions. They reject explanations that repeatedly fail. The process can be slow. Sometimes an apparently simple question takes decades to answer. Sometimes a new observation forces an old interpretation to be revised. That is not a weakness of astronomy. It is one of its defining strengths. The universe does not need to conform to our expectations. Our explanations must conform to the evidence. Webb is valuable precisely because it gives the evidence a greater reach. It is allowing humanity to examine eras that once existed mostly inside computer simulations and theoretical models, and the implications reach beyond any one discovery. If early galaxies formed rapidly, we learn more about the efficiency of gravity and star formation. If black holes grew rapidly, we learn about extreme accretion and the origins of massive black hole seeds. If planetary atmospheres show unexpected chemistry, we learn about the diversity of planetary systems. If stellar nurseries reveal unfamiliar structures, we learn how common or unusual the conditions that produced our own solar system may have been. Every observation becomes another constraint on the story, and gradually, the story becomes less about humanity trying to place itself at the center of the universe. Instead, it becomes a story about continuity. The same physical laws that govern the first stars govern stars today. The same elements forged inside ancient stellar interiors can become part of modern planets. These same photons that began their journeys billions of years ago can still arrive at a telescope near Earth. We are not separate from cosmic history. We are one of its later consequences. But Webb's observations raise an even larger question. If the universe could move from such a simple beginning to such extraordinary complexity, what other forms of structure might emerge in environments we have not yet explored? And how far into the future can the same physical processes continue? A telescope has a natural way of making the future feel distant. Every observation it makes is technically a record of the past. The more distant the object, the older the light. Yet the James Webb Space Telescope is also part of a much longer future in astronomy. Its mission will eventually end. Its instruments will eventually stop operating. Its observations will eventually become historical records themselves. And the questions it raises will continue long after the telescope falls silent. This is one of the quiet patterns of science. An instrument is built to answer one generation's questions. Its discoveries create questions for the next. Webb is no exception. Its operational life is limited by physical realities. The spacecraft carries propellant needed to maintain its orbit around the Sun-Earth L2 region and to control its orientation. That propellant is finite. The telescope also operates in an environment where tiny particles can strike its mirrors and gradually alter their surfaces. Radiation affects electronics. Mechanical components experience aging. No spacecraft lasts forever. But the end of Webb will not represent the end of infrared astronomy. In fact, Webb was never intended to be the final telescope of its kind. It is part of a sequence. Each generation extends the capabilities of the previous one. Hubble followed earlier space observatories. Webb followed Hubble in the infrared. Future observatories will eventually extend beyond Webb in sensitivity, resolution, wavelength coverage, or specialized capability. Some may be designed to study the earliest galaxies more efficiently. Others may focus on directly imaging planets around nearby stars. Some may search for atmospheric signatures with greater precision. Others may investigate the large-scale structure of the universe through enormous surveys. The future will likely involve many observatories rather than one universally dominant telescope. This matters because no single instrument can observe every wavelength or answer every question. Webb is extraordinarily powerful in infrared, but other parts of the electromagnetic spectrum reveal different physical processes. Radio observations can trace cold gas and molecular clouds. X-rays reveal extremely hot plasma and energetic black hole environments. Ultraviolet observations reveal hot stars and energetic processes. Visible light remains essential for studying many structures. Infrared observations add another layer. Together, these wavelengths create a more complete picture. The future of astronomy will increasingly depend on combining them. There is also another kind of future, the future of computation. Modern telescopes produce enormous quantities of data. A single observation may contain millions of individual measurements. Astronomers must distinguish real sources from noise. They must classify galaxies, estimate redshifts, model spectra, compare observations with simulations, search for rare objects. As datasets grow, computational methods become increasingly important. Machine learning may help identify patterns within enormous astronomical surveys. But these methods introduce their own questions. A computer can recognize a pattern without necessarily explaining its physical cause. An algorithm can classify an object without telling us why it has that appearance. The interpretation still depends on physics. The future will therefore not simply be about collecting more data. It will be about extracting more reliable knowledge from those data. This is especially important when searching for rare phenomena. Suppose astronomers are looking for the earliest galaxies. They may have millions of candidate sources, but only a handful that existed during the first few 100 million years. Finding those objects requires careful filtering. A false candidate can consume valuable observing time. A missed candidate can hide an important piece of cosmic history. The future of astronomy will therefore depend on better methods for deciding which questions deserve the most attention. And some of those questions may be impossible to answer with Webb alone. Consider the first stars. If population 3 stars remain difficult to identify directly, future observatories may need greater sensitivity or different wavelength capabilities. The first galaxies may be easier to detect than the individual stars within them. A telescope with a larger collecting area could potentially separate those signals more effectively, or an entirely different observational strategy may be required. The same is true for the origins of supermassive black holes. Webb can reveal their presence in the early universe, but understanding their birth may require observations of their surrounding gas, gravitational interactions, and growth histories across multiple wavelengths. The solution may not be another infrared telescope. It may be a network of instruments working together. This is how difficult scientific problems often evolve. The first instrument discovers a phenomenon. The second characterizes it. The third tests competing explanations. Eventually, the problem becomes a multidisciplinary investigation. The same process is already visible in exoplanet science. The first generation of exoplanet discoveries answered a basic question. Planets exist around other stars. Later observations began to measure their masses, sizes, and orbital properties. Now astronomers are studying atmospheres. The next stage may involve more precise atmospheric characterization and direct imaging of smaller planets. Eventually, researchers may be able to examine planets with physical conditions increasingly similar to those of Earth. But even then, the central question will remain difficult. What evidence would actually distinguish life from an unusual but entirely non-biological atmosphere? There is no single molecule that provides a universal answer. A future detection would need context, atmospheric chemistry, planetary temperature, stellar radiation, cloud structure, surface conditions, perhaps seasonal variation, perhaps atmospheric disequilibrium. Several independent clues would need to point toward the same explanation. This is why the search for life is not simply a technological race. It is also a problem of interpretation. The more capable the instruments become, the more carefully scientists must define what counts as evidence. There is another possibility that future observatories may explore: direct imaging. Webb can study some exoplanet atmospheres through techniques that do not require the planet to be fully separated from its star in an ordinary photograph. But directly imaging a small rocky planet beside a star like the Sun is extraordinarily difficult. The star can be billions of times brighter. The planet may appear only as a tiny point of reflected light. Future telescopes may use large mirrors, coronagraphs, star shades, or combinations of techniques to suppress starlight and reveal faint planets. If such systems become practical, astronomy could enter a new era. Instead of studying planetary atmospheres only through brief transits, astronomers could observe planets as individual worlds. They might track changes over time. They could study clouds, perhaps seasonal cycles, perhaps the distribution of gases, perhaps even surface properties under favorable conditions. This remains a future possibility, not a guaranteed outcome. The engineering challenges are immense, but the direction is clear. Webb has helped demonstrate what atmospheric spectroscopy can achieve. Future missions can build upon that experience. The same pattern applies to cosmology. Webb is probing the first galaxies. Future surveys will examine millions or billions of galaxies across enormous volumes of space. By mapping their positions and properties, astronomers can investigate how cosmic structure developed over time. They can compare observations with predictions from cosmological models. They can study dark matter through gravitational effects. They can investigate dark energy through the history of cosmic expansion. Here again, the future question may become more precise. Instead of asking what dark energy is in a general sense, astronomers may ask whether its properties have remained constant throughout cosmic history. If the answer is yes, certain models gain support. If the answer is no, the implications could be profound. But such conclusions will require multiple independent measurements. Astronomy becomes strongest when different methods converge on the same result. This is particularly important because the universe offers only one observable history. We cannot create a second universe with different initial conditions and compare the results. We cannot rerun cosmic history. We have one universe, one expansion history, one distribution of matter, one observable sky. That makes every independent measurement precious. Webb contributes one set of observations. Other telescopes contribute others. Together they create something much more powerful than any single instrument. A future astronomer may look back at Webb in much the same way that we now look back at earlier observatories, not as the telescope that solved the universe, but as the telescope that made certain questions unavoidable. That may ultimately be its greatest legacy. The telescope's most important discovery may not be one galaxy or one planet. It may be the realization that the early universe contains more structure than we had previously been able to see. And once that structure becomes visible, the next generation can ask deeper questions. How did the first stars ignite? How did the first black holes form? How quickly did galaxies assemble? How did the first chemical elements spread? How common were planetary systems during the early history of the Milky Way? How many worlds developed atmospheres? And among all those worlds, how often did chemistry become something more complicated? These questions may remain open for decades. Some may take centuries, Others may eventually prove impossible to answer completely. But scientific progress does not require every question to have a final answer. Sometimes the most valuable achievement is moving the boundary between ignorance and knowledge. Webb has done exactly that. It has moved the boundary, and as it moves, another boundary becomes visible beyond it. The universe that Webb can observe is not the whole universe. There are regions beyond our observable horizon. There are events whose light has not yet reached us. There are physical processes whose signatures are too faint to detect. There are questions that require instruments not yet designed. And there may be phenomena that no current theory anticipates. The future of astronomy therefore remains open. The Golden Mirror is one chapter. Future mirrors will continue the sentence. Perhaps they will find the first stars. Perhaps they will reveal how black holes acquired their enormous masses. Perhaps they will identify atmospheres unlike anything in our solar system. Perhaps they will discover that some of today's unanswered questions were based on assumptions that future observations will quietly replace. Or perhaps the universe will remain stranger still. That uncertainty is not something to fear. It is the reason there is still something to discover. And eventually, when future telescopes look back at the era of Webb, they may see what we now see when we look at the earliest observatories, a beginning, not an ending. Because every time humanity builds a better way to see the universe responds with another question. At the beginning of this journey, the idea seemed simple. A telescope looks at distant objects and makes them appear closer. That description is not wrong. It is simply incomplete. The James Webb Space Telescope has shown why. A distant galaxy does not merely appear smaller because it is far away. Its light has travelled across an expanding universe. The wavelengths have changed. The galaxy itself has changed during the billions of years since that light was emitted. And by the time those ancient photons reach Webb, they carry information about a universe that no longer exists in the same form. Distance has become time, and time has become evidence. This changes the meaning of what a telescope does. Webb does not physically travel into the ancient universe. It does not look backward through a window in space. It receives light. The past comes to us. That simple fact has extraordinary consequences. When Webb detects a galaxy that existed only a few 100 million years after the Big Bang, we are not seeing that galaxy as it would appear today. We are seeing it at the moment when its ancient light began its journey. The galaxy may now have merged with another system. Its stars may have evolved. Its black hole may have grown. Its structure may have been transformed beyond recognition. But the old light remains. For billions of years, it has carried a record of what once happened. And Webb is sensitive enough to receive some of those records. This brings us back to the belief with which the story began. Telescopes do not simply make distant things appear closer. They allow us to see different moments in cosmic history. The farther we look, the earlier the universe becomes. That is why Webb's enormous mirror and infrared instruments matter. They are not merely making the telescope more powerful. They are allowing it to cross a particular historical boundary. The earliest galaxies emit light that has been stretched far into the infrared. Their faintness requires a large collecting area. Their environments can be hidden by dust. Their physical properties require spectroscopy. The telescope's unusual design follows directly from these problems. The segmented mirror exists because a single enormous mirror could not fit inside its launch vehicle. The sunshield exists because the telescope must remain cold. The gold coating exists because the mirror must efficiently reflect infrared light. The distant orbit exists because the observatory needs a stable thermal environment. The deployment mechanisms exist because the telescope must unfold after launch. None of these features is arbitrary. They are solutions to the physical problem of observing ancient infrared light. And that realization changes how we see the spacecraft itself. Webb is not simply a beautiful machine. It is a physical argument. Its engineers are effectively saying that if we want to answer certain questions about the universe, this is the kind of machine those questions require. The telescope's history is therefore inseparable from the questions that created it. What were the first galaxies like? How quickly did stars form? How did black holes grow? How did the universe become chemically enriched? How did planets form around other stars? What kinds of atmospheres exist on distant worlds? These questions belong to different areas of astronomy, but Webb connects them through one fundamental resource: light. The same physical language appears again and again. A spectral line reveals an element. A redshift reveals cosmic expansion. An atmospheric absorption feature reveals a molecule. A faint infrared glow reveals warm dust. A changing brightness reveals an orbiting planet. A broad distribution of galaxies reveals cosmic structure. Light is not merely illumination, it is information, and the farther it travels, the older that information becomes. This is perhaps the most important idea Webb makes tangible. The night sky is not a single moment, it is a layered history. The moon is seen about a second after its light leaves its surface. The sun is seen roughly 8 minutes after its light leaves it. Nearby stars appear as they were years earlier. Nearby galaxies appear millions of years in the past. The most distant galaxies Webb observes appear billions of years in the past. The sky therefore contains different ages simultaneously. Look in one direction and you may see a star as it existed decades ago. Look much farther, and you may see a galaxy from before Earth existed. The universe presents its history across distance. Webb simply reaches farther into that archive, and yet the archive is incomplete. There is an era before the first stars that Webb cannot observe directly through ordinary starlight. There are objects too faint for its instruments. There are chemical signatures that remain ambiguous. There are black holes whose origins remain uncertain. There are galaxies whose histories can only be reconstructed indirectly. There are entire physical processes that may leave traces too subtle for current instruments. So even after everything Webb has accomplished, the original mystery remains: how did the universe move from simplicity toward complexity? We know some of the steps. Gravity gathered matter, stars formed, stars produced heavier elements, galaxies grew, black holes emerged, planets formed. Chemistry became richer, but the exact sequence, especially during the earliest periods, is still being assembled. The gaps matter. A few 100 million years may seem like a long time. On the scale of human history, it is almost unimaginably long. On the scale of cosmic evolution, it can be remarkably short. The fact that stars and galaxies already existed so early tells us that structure formation was efficient enough to operate rapidly. But efficiency alone does not explain every detail. The universe may have contained many small galaxies that we have not yet detected. Some may have been hidden by dust. Some may have been too faint. Some may have contributed to ionization without leaving easily identifiable signatures. The early cosmos may therefore be richer than the visible population suggests. This is why the story remains unfinished, and perhaps it should. There is a temptation to imagine that a sufficiently powerful telescope could eventually remove every mystery, but observation does not work that way. Better instruments reveal finer details. Finer details reveal new questions. A higher resolution image shows structures that a lower resolution image could not distinguish. A better spectrum reveals additional chemical lines. A larger survey reveals rare populations. Each improvement expands the amount of knowledge and the number of things that require explanation. The frontier moves outward. This is exactly what has happened with Webb. Before its launch, astronomers knew the early universe existed. They knew that galaxies had formed. They knew that the first stars must have appeared at some point, but they had limited direct observations of the earlier stages. Now, the early universe contains actual galaxies that can be measured. Some existed at extraordinarily early times. Some contain evidence of active black holes. Some show unexpected chemical or spectral properties. Some appear more luminous than simple models anticipated. Others fit comfortably within revised models. The picture is becoming more detailed, and as the details accumulate, the broad story remains surprisingly coherent. The universe began hot and dense. It expanded. It cooled. Matter gathered under gravity. Stars formed. Galaxies emerged. Stars created heavier elements. Those elements became part of later generations. Planetary systems formed. And eventually, on at least one small world, chemistry became life. Webb does not prove every part of that sequence. It does not observe the entire chain directly, but it provides new evidence for many of its stages. It allows the broad story to be tested against observations from epochs that were once almost inaccessible. That is a remarkable achievement. Yet perhaps the most beautiful part is that the telescope does not need to know what it will find. Its mirror has no preference for one theory. Its detectors do not care whether a galaxy confirms a prediction or challenges it. The photons arrive. The instruments measure them. Scientists compare those measurements with ideas, and the universe gets the final word. That is where the story has brought us. back to the beginning. Not the beginning of the universe, the beginning of our questions. We thought a telescope simply helped us see farther. Now we know that seeing farther means seeing earlier, and seeing earlier means recovering physical evidence from a time when the universe itself was still becoming what it is today. The James Webb Space Telescope was built to reach into that ancient light. It has done so. But the deeper it looks, the more obvious another truth becomes. The first light we can detect is not necessarily the first light that ever existed. There may always be another layer beyond the last one we can see, and if every boundary reveals another boundary, then perhaps the most important question is no longer how far Webb can see. It is what we will build when we reach the point where Webb can see no farther. There is something quietly remarkable about a photon. It does not know where it is going. It does not know that billions of years will pass before it reaches its destination. It simply travels. Some photons begin their journeys inside the atmospheres of distant planets. Some emerge from clouds where stars are being born. Some leave the hot material surrounding a growing black hole. And some began their journeys when the universe itself was still young. They travel through expanding space. The stars that produce them change. Galaxies merge. New stars are born. Planets form. Entire civilizations rise and disappear on worlds that are, from the perspective of cosmic time, almost impossibly brief. The photons continue. Eventually, some reach a mirror. For a small number of them, that mirror is part of the James Webb Space Telescope. The photon strikes one of 18 segments of beryllium coated with gold. It is reflected, then reflected again. Its path is focused toward an instrument designed to measure infrared light. There, after a journey longer than almost anything we can easily comprehend, the ancient signal becomes a number, a measurement, a spectrum, a tiny piece of data, and from those pieces, human beings begin reconstructing a vanished universe. That process is extraordinary partly because it is so ordinary. There is no special boundary between the ancient light and the present. The same laws of physics connect them. The light does not become a memory merely because it is old. It remains physical information. Webb receives it, we interpret it, and suddenly a galaxy that existed billions of years ago becomes part of our present understanding. This is what the telescope has really changed. Not the age of the universe, not the distance between the stars, our access to the evidence. Before Webb, the earliest universe was already part of scientific theory. Now more of that ancient world has become observable. The first galaxies are no longer simply ideas drawn on computer screens. Some can be measured. Their light can be separated. Their chemical signatures can be examined. Their black holes can be investigated. Their environments can be compared. And still, the mystery remains, because every answer has exposed another question. How did the first stars form? How did their light escape? How did the first galaxies grow? How did black holes become massive so quickly? How did simple primordial material become the chemical richness required for planets? How many worlds formed around the stars that followed? And somewhere among those worlds, how often did the chemistry of matter become something we would recognize as life? We do not yet know. Perhaps some of these questions will be answered by future observations. Perhaps some will require instruments that have not yet been imagined. Perhaps some answers will arrive through theories that are still being developed. And perhaps some questions will remain beyond our reach. There is no failure in that possibility. A universe without unanswered questions would be a very different universe from the one we inhabit. The James Webb Space Telescope was never a machine for reaching the final page of cosmic history. It was built to open another chapter. Its golden mirror is already part of that history. One day, the telescope itself will become quiet. Its last observation will become part of an archive. Future astronomers may examine those old measurements in the same way we now study observations made by earlier generations. They may understand some of Webb's discoveries more clearly than we can. They may reinterpret others. They may find patterns in its data that no one has yet recognized. That is another quiet feature of science. The significance of an observation does not always arrive at the same time as the observation itself. Sometimes knowledge has to wait for the right question. So perhaps the story of Webb is not really a story about reaching the edge. It is a story about learning where the edge has moved. Every time we see farther, the darkness becomes more detailed. Every time we understand more, the unknown becomes more precise. And every time we answer one question, another waits beyond it. The universe has been expanding for billions of years. Light has been crossing it for almost as long. Some of that light is still travelling toward places it has not yet reached. Some of it has already reached us. Some of it has become the images and spectra that now fill scientific archives, and some of it is still on its way. There are galaxies whose ancient light has not yet arrived. There are worlds whose atmospheres have never been measured. There are stars that have not yet formed. There are structures whose existence we do not yet know to ask about. The night sky is therefore not finished. It is still arriving. Perhaps that is the quietest lesson of the James Webb Space Telescope. We are not looking at a universe that has already revealed everything it contains. We are receiving it gradually, photon by photon, year by year, generation by generation, and somewhere, far beyond the reach of the human eye, another ancient beam of light is moving through the darkness. It began before Earth existed, before the Sun, before our galaxy had the shape it has today. It carries a record of something that happened long ago. We do not know exactly what that record contains. We only know that, eventually, if the light reaches us, and if we build instruments sensitive enough to receive it, we may learn something from it. Until then, the question remains suspended in the darkness. How much of the universe's history is already travelling toward us, carrying answers to questions we have not yet learned how to ask?